The biggest mega projects are reaching an unprecedented scale. Record-breaking tunnel, bridge, and skyscraper projects are reshaping landscapes worldwide. It's time to dive into these projects, discovering how engineers redefine construction standards. Starting with the massive Kiosk Hydroelectric Project. This project has a total capacity of 695 megawatts and is designed to harness the power of the Nelson River to generate renewable energy. The primary structure of the Kiosk Hydroelectric Project is the generating station, which consists of a concrete powerhouse housing 7 turbine generator units. The Kiosk project includes 7 dams with a combined length of nearly 24 kilometers and 2 large dikes designed to control water flow and create the necessary head for power generation. The powerhouse and spillway structure were constructed using large quantities of reinforced concrete, with the total concrete volume used in the project exceeding 700,000 cubic meters. The turbine and generator units at Kiosk are Kaplan turbines, chosen for their efficiency in harnessing the variable flow of the Nelson River. The installation process included the careful alignment of the turbine shafts and the precise calibration of the generator units to ensure optimal performance.
It's time to move on to neighboring country Denmark, where the Great Belt Bridge stands as the tallest bridge in the country. Officially known as the East Bridge, it boasts the world's 3rd longest suspension bridge span, with a monumental stretch of 1624 meters between its towers, which themselves ascend to a majestic height of 254 meters. This bridge is part of the Great Belt Fixed Link, a multi-structure project that also includes a box girder bridge and a tunnel collectively spanning a comprehensive length of 18 kilometers. Constructed at a cost of over $4 billion, it was an investment that streamlined travel drastically, cutting down transportation time between Copenhagen and Odense by more than an hour. The East Bridge carries more than 27,000 vehicles each day, effectively doubling the potential for inter-island commerce and connectivity. Its construction required 19 concrete piers, the largest of which weighs approximately 530,000 tons. But we have to talk about the construction of Terminal 3 at Frankfurt International Airport. The new terminal, designed by the architectural firm GMP, will incorporate state-of-the-art technology and modern design elements to create a world-class facility. It will feature 3 piers, each equipped with numerous boarding gates, lounges, and retail spaces. The terminal's design emphasizes sustainability and energy efficiency, with extensive use of natural light, energy-saving systems, and environmentally friendly materials. Construction of Terminal 3 began in 2015, with the project reaching completion in 2023. The terminal represents a significant investment, estimated at around $4.5 billion. One of the primary challenges has been managing construction activities while maintaining normal airport operations. The project team has implemented advanced construction techniques and rigorous planning to ensure minimal disruption to daily operations. Terminal 3 is designed to enhance passenger comfort and convenience. The spacious terminal will offer a variety of amenities, including dining options, shopping areas, and relaxation zones. High-speed internet, comfortable seating, and abundant charging stations will cater to the needs of modern travelers. The terminal will also feature advanced security and check-in systems to streamline the passenger experience and reduce wait times. The construction of Terminal 3 involves the use of innovative building techniques, such as prefabrication and modular construction. These methods allow for faster construction times and reduced environmental impact. The project team has also employed advanced project management software to coordinate activities and ensure that the project stays on schedule and within budget. The Intuit Dome is a state-of-the-art sports and entertainment arena currently under construction in Los Angeles, set to be the new home for the Los Angeles Clippers NBA team. This $1.8 billion project features a futuristic design with a seating capacity of 18,000, providing fans with an unparalleled viewing experience. The construction incorporates advanced engineering techniques, such as a cantilevered steel roof structure that eliminates the need for interior columns, ensuring unobstructed views from every seat. The arena is equipped with cutting-edge technology, including a high-definition scoreboard that wraps around the entire arena and an advanced sound system for an immersive audio experience. One of the major challenges is the integration of sustainable building practices. The Intuit Dome aims to be a net-zero energy building, utilizing a combination of solar panels, energy-efficient systems, and innovative water conservation methods. The project also includes the construction of a multi-story parking structure and extensive landscaping with native plants to create a welcoming environment for fans. Advanced construction methods, such as prefabrication and modular assembly, are used to streamline the building process and reduce construction time. The arena will also feature numerous amenities, including luxury suites, a training facility, and spaces for community events. Once completed, the Intuit Dome will not only serve as a premier sports venue, but also as a catalyst for economic development in the surrounding area, creating jobs and attracting visitors to Los Angeles. The project underscores the importance of integrating modern design with sustainability, setting a new standard for future sports facilities worldwide. The Intuit Dome is poised to become a landmark in Los Angeles, drawing millions of visitors annually and significantly boosting the local economy through tourism and event hosting. The project also includes significant community engagement initiatives, ensuring that the benefits of the new arena extend to the local population through improved infrastructure and social programs. The construction utilizes advanced machinery, including mobile cranes, steel erection rigs, and prefabrication technology, to ensure precise and efficient assembly of the structure.
It's time to travel over to the country of China. Here, the Shanghai-Nantong Yangtze River Bridge is a major infrastructure project designed to improve connectivity between Shanghai and Nantong. This $3.5 billion bridge spans 11 kilometers across the Yangtze River, making it one of the longest cable-stayed bridges in the world. Construction of the bridge began in 2014, with the project completed in 2020. One of the primary engineering challenges was constructing a bridge that would accommodate both road and rail traffic. The bridge features a dual-use design, with a 6-lane highway on the upper deck and a 4-track railway on the lower deck. This design requires advanced engineering techniques to ensure the bridge's stability and load-bearing capacity. The bridge's main span is 1,092 meters long, supported by 2 towers that reach a height of 325 meters. These towers are among the tallest bridge towers in the world, requiring precise engineering and construction techniques. The towers are constructed using high-strength concrete and reinforced steel to withstand the heavy loads and environmental conditions of the Yangtze River. One of the key innovations in constructing the Shanghai-Nantong Yangtze River Bridge is the use of large-diameter steel cables to support the bridge deck. These cables are made from high-strength steel and can bear the significant weight of the combined road and rail traffic. The cables are anchored in massive concrete blocks on either side of the river, providing the necessary tension to support the bridge deck. The construction of the bridge also involved extensive foundation work, using deep-water drilling techniques to create stable foundations in the riverbed. These foundations are designed to resist the strong currents and seismic activity of the region, ensuring the long-term stability and safety of the bridge. Engineers employed advanced geotechnical analysis and testing to ensure the foundations could withstand the dynamic forces exerted by the river in passing trains. We have to travel all the way over to Denmark next to talk about the Copenhagen Metro project. This system has expanded a lot over the years, most notably with the City Ringen line, which became operational in 2019. The construction involved extensive tunneling through the city's dense urban environments. The underground sections were built using tunnel boring machines, which excavated twin tunnels with a diameter of approximately 5.5 meters each. The TBMs used for the City Ringen line were equipped with earth pressure balance technology, which maintained stability in the tunnel face while minimizing ground settlement. Each TBM could excavate up to 20 meters of tunnel per day, and they worked 24 hours a day to complete the twin 15.5-kilometer-long tunnels. The tunnel linings were constructed using precast concrete segments, which were manufactured off-site and assembled as the TBM advanced. Each ring of the tunnel lining consisted of 6 segments weighing up to 15 tons each. These segments were bolted together to form a watertight and structurally sound tunnel. The stations were built using a top-down construction method, which allowed the excavation of the station boxes while minimizing disruption at a street level. The walls of these stations were made using reinforced concrete diaphragm walls. After the station box was completed, it was connected to the tunnel using cut-and-cover methods or mined cross passages depending on the station's location and depth. The Metro's tracks are set on a floating slab trackbed, which reduces vibrations and noise while providing a stable and smooth ride for passengers. The rail system uses standard gauge tracks, with steel rails continuously welded to minimize maintenance needs. Over 3 million cubic meters of material were excavated and removed during the project, requiring a coordinated effort between contractors and local authorities.
It's now time to check out the Petronas Twin Towers in Kuala Lumpur, Malaysia. Reaching a staggering height of 452 meters, this project is the tallest twin structure in the world and surpasses the Willis Tower in Chicago by 10 meters. These architectural marvels held the title of the tallest buildings in the world from 1998 to 24 until surpassed by Taipei 101. Constructed using 33,000 tons of steel and 160,000 cubic meters of concrete, each tower is supported by a 120-meter deep foundation, which is among the deepest for any building. The design, a brainchild of Argentine-American architect Cesar Pelli, was inspired by traditional Islamic art reflecting Malaysia's cultural heritage, with a floor plan based on an 8-pointed star. The towers are linked by a double-decker skybridge at the 41st and 42nd floors, which is the highest two-story bridge in the world. Featuring 88 floors of office space, the towers house the headquarters of Petronas, Malaysia's national petroleum corporation, as well as other corporations. The construction of the Petronas Twin Towers employed a cutting-edge curtain wall system that is designed to reduce heat and enable energy-efficient cooling. Let's talk about the Johan Sverdrup oil field in Norway next. Located approximately 87 miles west of Stavanger, the project involves the construction of multiple offshore platforms, pipelines, and support infrastructure to extract and transport oil from the field. Development of the Johan Sverdrup oil field began in 2015, with production starting in 2019. The project represents a substantial investment, estimated at around $17 billion. The oil field has estimated reserves of 2.7 billion barrels of oil equivalent, making it one of the most significant discoveries in the North Sea in recent decades. The construction of the Johan Sverdrup oil field required advanced engineering and construction techniques to address the challenges of operating in the harsh and unpredictable North Sea environment. The project features a network of platforms, including a processing platform, a riser platform, and a living quarters platform, all connected by bridges to create an integrated offshore complex. The foundation work for the platforms involved driving large steel piles deep into the seabed to ensure stability. Each pile was installed using specialized pile driving equipment capable of operating in deep water. The piles were then filled with concrete to enhance their load-bearing capacity and resistance to corrosion. Heavy lift vessels played a crucial role in the construction process. These vessels transported large prefabricated modules, including topsides and jackets, from fabrication yards to the installation site. The use of heavy lift vessels allowed for the efficient transport and precise placement of these massive components. Each platform was equipped with advanced drilling and processing equipment, designed to maximize efficiency and minimize downtime. The installation of pipelines to transport oil and gas from the field to onshore facilities was another critical aspect of the project. These pipelines were laid using specialized pipelay vessels, which can handle the complex seabed topography and ensure the integrity of the pipeline system. The Johan Sverdrup oil field is expected to produce oil for several decades, contributing significantly to Norway's energy production and economic growth. The Stad Ship Tunnel in Norway is an ambitious maritime infrastructure project designed to improve navigational safety and efficiency along the Norwegian coast. The tunnel, measuring 1.1 mile in length, will allow ships to bypass the hazardous Stad Peninsula, known for its treacherous waters and frequent storms. The construction involves excavating through solid rock, requiring advanced drilling and blasting techniques. One of the primary challenges is managing the removal and disposal of the excavated material, which is addressed through a combination of conveyor systems and specialized transport vehicles. The tunnel's design includes a wide and tall cross-section to accommodate large vessels, with reinforced concrete lining to ensure structural integrity. Advanced engineering techniques, such as the use of waterproofing membranes and drainage systems, are employed to manage groundwater and prevent seepage. The project also incorporates state-of-the-art navigation and safety systems, including automated traffic management and emergency response facilities. Once completed, the Stad Ship Tunnel will significantly enhance maritime safety, reduce travel time, and promote economic development by providing a reliable and efficient passage for shipping along Norway's coast. The tunnel is expected to become a major attraction, drawing tourists and boosting local economies. The project exemplifies Norway's innovative approach to solving transportation challenges and improving maritime infrastructure. The tunnel will also reduce the environmental impact of shipping by providing a safer and more direct route, minimizing the risk of accidents and spills. Additionally, the project will create job opportunities during the construction phase and beyond, contributing to the economic growth of the region. The construction process employs specialized tunneling equipment, including tunnel boring machines, rock drilling rigs, and high-capacity conveyor systems to manage the excavation and transport of materials efficiently.
Let's move over to the United States next, where the Silicon Valley Clean Water Project is located. This $500 million project involves constructing new treatment facilities and rehabilitating existing infrastructure to improve the efficiency and sustainability of the wastewater treatment process. The project includes the construction of a new wastewater treatment plant, which features advanced treatment technologies such as membrane bioreactors and ultraviolet disinfection. Membrane bioreactors are a combination of a biological treatment process and membrane filtration. They offer superior treatment performance compared to conventional methods, providing high-quality effluents by filtering out fine particles and microorganisms. Ultraviolet disinfection is another advanced technology employed by the project. UV disinfection involves exposing treated wastewater to ultraviolet light, which inactivates pathogens and microorganisms by damaging their DNA. This method is highly effective and does not involve the use of chemicals, making it an environmentally friendly alternative to traditional chlorination. This project also involves the rehabilitation of existing infrastructures, including replacing aging pipelines and upgrading pump stations. The pipelines are critical for transporting wastewater to and from the treatment plant. Engineers use trenchless technology such as cured-in-place pipelining to rehabilitate the pipelines without extensive excavation. This method involves inserting a resin-coated liner into the existing pipe and curing it in place, creating a new, durable pipe within the old one. Another critical component of the project is the construction of new storage and equalization tanks. These tanks are designed to manage the flow variations in the wastewater treatment process, ensuring a consistent and controlled flow of wastewater through the treatment plant. The construction of the Silicon Valley Clean Water Project also involves extensive earthworks to prepare the site for new facilities. This includes land grading excavation and soil stabilization. Land grading involves reshaping the land surface to achieve the desired elevations and slopes for the treatment plant. But we haven't talked about the Taiwan high-speed rail megaproject yet. Stretching approximately 350 kilometers from Taipei to the north of Zhoushan in the south, the rail project significantly reduces travel times across the island, with trains reaching speeds up to 186 miles per hour. One notable aspect of the rail project is the extensive use of elevated viaducts. Approximately 73% of the line runs on elevated structures, totaling around 251 kilometers. These viaducts were constructed using pre-stressed concrete segments, each typically 30 meters long and weighing around 800 tons. The segments were precast and then transported to the construction site, where they were then assembled using large overhead gantry cranes. In addition to the viaducts, the high-speed rail also required the construction of numerous tunnels, totaling 48 kilometers on the line. The longest tunnel, the Baguashan Tunnel, spans 7.4 kilometers. Tunneling through Taiwan's varied geological formations required the use of different excavation techniques, such as the new Austrian tunneling method and tunnel boring machines. Another critical engineering component of the project is its earthquake detection and safety system. Given Taiwan's location on the Pacific Ring of Fire, seismic activity is a significant concern. The rail project is equipped with a network of seismometers along the route, which can detect ground motion and trigger an automatic braking system on the trains within seconds. The track system itself is a combination of continuously welded rails and ballastless track technology. The tracks are laid on a concrete bed rather than the traditional gravel ballast, which provides a more stable foundation for high-speed travel. The power supply for the THSR is provided by a dedicated overhead catenary system, which drives electricity to the trains through a network of substations strategically placed along the route. The power system is designed to ensure a consistent supply of electricity even during peak operational periods and includes redundant systems to maintain operations in the event of power failure.
It's time to visit Tokyo next for the Tokyo Skytree. Towering at 634 meters, it was completed in 2012 to serve as a primary television and radio broadcast site for the Kanto region, ensuring clearer transmission as high-rise buildings proliferated. Constructed with about 36,000 tons of steel, Tokyo Skytree features a unique seismic proofing design with a central concrete column independently secured from the surrounding steel frame, a method inspired by ancient pagodas which allows the structure to withstand earthquakes with minimal sway. The tower's color, officially called Skytree White, is based on a traditional Japanese indigo blue hue, blending modern design with traditional aesthetic considerations. The lighting of the Skytree alternates between the Iki sky blue and Miyabi purple, inspired by the patterns of Japanese folding fans, which illuminate the tower beautifully at night. Tokyo Skytree has two observation decks at heights of 350 meters and 450 meters, offering panoramic views of Tokyo and, on clear days, Mount Fuji. The base of the Skytree is a bustling commercial hub named Tokyo Solamachi, which includes over 300 shops and restaurants. Let's investigate the Plock-Olfen complex located in Poland next. This project involves the construction of new production units, storage facilities, and support infrastructure to enhance the complex's output and efficiency. Construction of the complex began in 2020, with it being completed in 2023. The project represents a significant investment, estimated at around $3 billion. One of the primary objectives is to increase the production of ethylene and propylene, which are essential feedstocks for the chemical industry. These products are used in the manufacturing of plastics, synthetic rubber, and other industrial materials. The complex features state-of-the-art production units equipped with advanced technology to ensure efficient and environmentally friendly operations. The project includes the construction of a new steam cracker, which will break down hydrocarbons into ethylene and propylene using high-temperature steam. This process is critical for producing the raw materials needed for various chemical products. The new facilities will incorporate energy-efficient technologies and systems to reduce emissions and minimize environmental impact. The project also includes measures to manage waste and water use, ensuring that the complex operates in an environmentally responsible manner. One of the challenges of the project has been coordinating the construction activities while ensuring the continued operation of the existing facilities at the Plock site. The project team has employed advanced project management techniques to plan and execute the construction, minimizing disruptions and ensuring that the project stays on schedule and within budget. The Westgate Tunnel project in Melbourne is a significant infrastructure initiative designed to alleviate traffic congestion and improve travel times in one of Australia's busiest urban areas. The $6.7 billion project involves constructing a 4-mile toll road with twin tunnels under Yarraville, a new bridge over the Maribyrnong River, and the widening of the Westgate Freeway. The project is a key component of the broader Victorian government's infrastructure plan to modernize and enhance the city's transport network. The tunnels will be constructed using massive tunnel boring machines, each weighing 4,000 tons and stretching 300 feet long. These tunnel boring machines are designed to excavate through diverse geological conditions, including soft clays and basalt rock, while simultaneously installing precast concrete segments to form the tunnel walls. Managing the disposal of the enormous volumes of excavated material is a key challenge, and this will be transported to designated sites for reuse or environmentally safe disposal. Advanced ventilation and air quality monitoring systems will ensure the safety of workers and the surrounding community. Noise and vibration mitigation measures are crucial to minimize the impact on nearby residents. The new cable-stayed bridge over the Maribyrnong River is designed to accommodate increased traffic volumes and enhance structural resilience against seismic activities. The project's integration of smart traffic management systems aims to optimize traffic flow and reduce congestion. Upon completion, the Westgate Tunnel is expected to significantly cut travel times, reduce congestion on the Westgate Bridge, and provide a much-needed alternative route for Melbourne's commuters and freight transport. The project also promises to enhance Melbourne's transport network by creating new cycling and pedestrian pathways, connecting key parts of the city and contributing to a more sustainable urban environment. Additionally, the construction phase is expected to generate thousands of jobs, providing a significant boost to the local economy.
But what about the International Thermonuclear Experimental Reactor project located in France? Located in Saint-Paul-les-Durance, this international project involves 35 countries and has an estimated cost of around $25 billion. Construction of the project began in 2010, with the project entering the assembly phase in 2020. The reactor is designed to produce 500 megawatts of fusion power from an input of just 50 megawatts, achieving a 10-fold energy gain. which would be groundbreaking of a milestone in fusion technology. The primary construction challenge is the sheer scale and complexity of the reactor components, many of which are being manufactured and assembled for the first time. The core of the project is the tokamak, a donut-shaped vacuum chamber where the fusion reaction occurs. The tokamak must withstand extreme conditions, including temperatures up to 150 million degrees Celsius, 10 times hotter than the core of the Sun. This requires using superconducting magnets to create powerful magnetic fields that confine the hot plasma within the chamber, preventing it from contacting the walls. The construction of these superconducting magnets is a major engineering feat. Each magnet, known as a toroidal field coil, weighs around 360 tons and comprises several kilometers of superconducting cable. These cables are made from a special alloy that becomes superconducting at very low temperatures, maintained by cooling systems using liquid helium. The project also involves constructing numerous supporting facilities, including cryogenic plants, cooling towers, and electrical substations. These facilities are essential for maintaining the reactor's operation and ensuring the safety and stability of the fusion process. One of the key innovations in the project is the use of remote handling systems for maintenance and repairs. Given the extreme conditions inside the tokamak, human access is impossible, necessitating the development of robotic systems capable of performing complex tasks with high precision. These systems are designed to operate in the harsh environment of the reactor, handling radioactive materials and high temperatures. It's time to move over to Abu Dhabi for the next mega project. The Noor Abu Dhabi solar plant represents one of the largest single-site power plants in the world. Located in the Swahan region, the project was completed in 2019. The plant has a capacity of 1.2 gigawatts, producing enough electricity to power approximately 90,000 homes and reducing the country's carbon emissions by 1 million metric tons annually. One of the most impressive aspects of the plant is its sheer scale. The site covers an area of approximately 3 square miles, making it one of the largest in terms of both capacity and physical footprint. The plant consists of 3.2 million solar panels, which were installed across the vast desert landscape. These panels are mounted on single-axis trackers, which allows them to follow the sun's path throughout the day, optimizing the angle of incidence. The plant uses polycrystalline silicon photovoltaic panels known for their durability and efficiency in high-temperature environments. The panels are capable of withstanding temperatures that regularly exceed 104 degrees Fahrenheit. A critical aspect was the development of the supporting infrastructure, including the electrical grid connections required to transmit the generated power to the national grid. This involved laying extensive underground cables and building substations to manage the distribution of electricity. To manage the operation of such a large number of solar panels, the plant is equipped with an advanced monitoring and control system that collects data from sensors on each panel, allowing for real-time monitoring of performance. Given the sandy and unstable soil conditions typical of desert environments, special attention was required to ensure that the panel mounts were securely anchored. This involved extensive geotechnical surveys and the use of deep pile foundations in some areas to provide the necessary stability. The transportation of 3.2 million solar panels and associated hardware to the remote desert site required detailed planning and coordination. The solar plant also incorporates water-saving technologies in its cleaning processes. Given the scarcity of water in the region, traditional cleaning methods that rely heavily on water were not feasible. Instead, the plant employs dry cleaning robots to maintain the cleanliness of the panels.
Making our way back to France, it's time to talk about the Millau Viaduct. Soaring to a height of 343 meters, it holds the title of the world's tallest cable-stayed bridge. The viaduct spans 2460 meters with the longest single span reaching 342 meters and a deck width of 32 meters. It features 7 concrete piers, with the tallest pier standing at 245 meters high, which is more than twice the height of the Statue of Liberty from base to torch. The bridge was designed by the British architect Norman Foster and French structural engineer Michel Verlejux. The construction, completed in just 3 years and opened in 2004, aimed to alleviate summer traffic congestion on the route from Paris to Spain, which it has successfully done by shortening travel time by several hours during peak periods. The viaduct not only serves a practical transport function, connecting the Clermont-Ferrand to Béziers and Montpellier, but also acts as a tourist attraction in its own right. Approximately 20,000 vehicles cross the viaduct each day, and its construction has boosted local economies by increasing accessibility and reducing transportation costs. we have to travel over to Austria for our next project. The Koralm Tunnel is one of the most ambitious railway infrastructure projects in Europe. This 20-mile-long tunnel, part of the Koralm Railway, will connect the cities of Graz and Klagenfurt, significantly reducing travel time and enhancing connectivity in the region. The tunnel passes through the Eastern Alps, making its construction a remarkable engineering feat. Construction of the Koralm Tunnel began in 2008, with completion expected by 2026. The project involves a substantial investment, estimated at around $5.4 billion. One of the primary challenges has been tunneling through the complex geological conditions of the Alps, which requires advanced tunneling techniques and machinery. The tunnel will feature twin tubes, each with a diameter of around 30 feet, allowing for separate tracks for trains traveling in opposite directions. The design includes state-of-the-art safety systems, such as emergency exits, ventilation systems, and fire protection measures. These features are essential to ensure the safety and reliability of the tunnel, given its length and the volume of traffic it will handle. The construction of the Koralm Tunnel involves the use of tunnel boring machines, which are capable of excavating through rock and soil with precision. The machines are equipped with cutting-edge technology to manage the challenges posed by the varying geological conditions. The project also includes the construction of access tunnels, ventilation shafts, and support structures to facilitate the excavation and operation of the main tunnels. Once completed, the tunnel will reduce travel time between Graz and Klagenfurt to just 45 minutes, compared to the current 3-hour journey by car. The new Everton Stadium, also known as Bramley Moor Dock Stadium, is a landmark development for Everton Football Club in Liverpool, United Kingdom. This 50-20-seat stadium is being constructed on the historic Bramley Moor Dock, a UNESCO World Heritage Site, blending modern architecture with the area's rich industrial heritage. The project involves extensive groundworks to stabilize the dock, including the use of advanced piling techniques and ground improvement methods to ensure a solid foundation. One of the major engineering challenges is preserving the historic dock wall while integrating it into the stadium's design. The construction also includes a complex drainage system to manage water levels and prevent flooding. The stadium features a striking brick facade, echoing Liverpool's historic buildings, and a steep, single-tier home stand to enhance the matchday atmosphere. Inside, the stadium is equipped with state-of-the-art facilities, including hospitality suites, retail spaces, and a museum celebrating the club's history. Advanced construction techniques, such as the use of prefabricated components and modular construction, are employed to ensure efficiency and precision. Sustainability is a key focus, with the project incorporating renewable energy sources, energy-efficient systems, and sustainable materials. The construction also emphasizes the use of local materials and labor, supporting the regional economy. Once completed, the new Everton Stadium will not only provide a world-class venue for football, but also serve as a catalyst for the regeneration of the surrounding area, creating jobs and boosting the local economy. The stadium is set to become an iconic landmark in Liverpool, attracting tourists and sports enthusiasts from around the world. The project also includes community engagement initiatives, ensuring that the new stadium benefits the local population through improved infrastructure and social programs. Additionally, the stadium's design incorporates advanced acoustics and lighting systems, enhancing the overall spectator experience and making it a premier venue for various events beyond football. The construction process utilizes heavy machinery such as pile drivers, concrete mixers, and prefabrication assembly lines to ensure timely and accurate completion of the project.
We move over to Australia next for the Shell Prelude FLNG megaproject. This $12.6 billion project involves constructing a massive floating platform, which is the largest floating structure ever built. The FLNG facility is 488 meters long, 74 meters wide, and weighs approximately 600,000 tons when fully loaded. The hull of the platform was constructed using high-strength steel to withstand the forces exerted by the waves, wind, and currents. The steel plates were fabricated in sections and then assembled onto large blocks, which were transported to the construction site and welded together. One of the key components of the FLNG facility is the topside, which houses the gas processing, liquefaction, and storage equipment. The topside modules were constructed using a modular approach, where each module was fabricated and pre-assembled off-site and then transported to the construction site for installation. The liquefaction process involves cooling the natural gas to minus 162 degrees Celsius, converting it into a liquid form for storage transport. The FLNG facility is equipped with advanced liquefaction technology, including cryogenic heat exchangers and refrigeration units. These systems are designed to operate efficiently and reliably in the challenging offshore environment. The construction of the facility also involved installing subsea infrastructure to connect the platform to the gas fields. This includes installation of subsea walls, flow lines, and risers, which transport the natural gas from the seabed to the platform. One of the key innovations in the project is using dynamic positioning technology to maintain the platform's position without requiring anchoring or mooring lines. The DP system uses thrusters and advanced control algorithms to counteract the forces of wind, waves, and currents, ensuring the platform remains stable and secure. But we have to talk about the Ottawa LRT megaproject. This ambitious project was initiated to improve public transport in Canada's capital and reduce congestion on city streets. The Confederation Line, which spans 12.5 kilometers and includes 13 stations, was constructed between 2013 and 2019. A major challenge in the LRT's construction was developing the 2.5-kilometer downtown tunnel, which runs beneath some of the city's most densely built areas. The tunneling process employed the sequential excavation method, which allowed for careful excavation and support installation in the variable and unstable geological conditions. The tunnel required the excavation of over 300,000 cubic meters of material, much of which was done through conventional drill and blast techniques. Given Ottawa's harsh winters, the tunnel design had to account for freeze-thaw cycles and groundwater management, requiring advanced engineering solutions to prevent leaks. Another key engineering component of the Ottawa LRT was constructing the track infrastructure. The Confederation Line uses standard gauge tracks, and the rail system was built to accommodate modern light rail vehicles manufactured by Alstom. These LRVs are designed to operate efficiently in Ottawa's cold climate, with heated floors, enhanced insulation, and resilient braking systems that can handle ice and snow. Each station along the line features platform screen doors, which are not a safety feature, but also help to regulate temperature in the underground stations during extreme weather. The project also included the construction of a maintenance and storage facility located at the Belfast Yards, which covers over 4 hectares. This facility is equipped with advanced diagnostic and repair equipment to service the LRV fleet. One of the more complex elements of the project was integrating the LRT with existing transit infrastructure, including bus routes and the Trillium Line. The Confederation Line station were designed to facilitate smooth transfer between modes of transport. The integration also involved the construction of a new busy bus terminal and reconfiguration of existing routes to optimize the transit network's overall efficiency.
Crossing the globe, we travel to the United Kingdom for the tallest building in the country. The Shard rises majestically to a height of 310 meters, making it the tallest building in the country and the 4th tallest in Europe. Its 95 stories are encased in 11,000 glass panels, covering a total surface area of 56,000 square meters, which is enough to cover 8 football pitches. This neo-futuristic skyscraper, completed in 2012, was designed by the renowned Italian architect Renzo Piano, who envisioned it as a vertical city. The Shard houses offices, luxury residences, a 5-star hotel, and multiple top-tier restaurants, all offering panoramic views of London. The construction of the Shard was a monumental task, utilizing 243,000 cubic meters of concrete and 36,000 tons of steel. This structural marvel can accommodate up to 8,500 people at any one time, roughly equivalent to the population of a small town. Visitors can ascend to the observation deck, located on the 72nd floor, which offers an unrivaled 360-degree view of the city, stretching up to 64 kilometers on a clear day. The Shard's dynamic facade reflects the changing skies, seamlessly integrating the building into the fabric of London while minimizing heat absorption through its energy-efficient glass. It's time to talk about the Hermitage Plaza in France, a transformative skyscraper project in Paris's La Défense district. Comprising 2 towers reaching 320 and 240 meters respectively, the project aims to integrate residential, office, and commercial spaces. Designed by renowned architect Norman Foster, This development has been in construction since 2019, with an expected completion date in 2025. Constructing such ambitious towers in the heart of Paris requires overcoming numerous engineering challenges. To start, the foundation work involved extensive excavation and the use of slurry walls to ensure stability in the densely populated urban area. The foundations reach deep into the ground to anchor the skyscrapers securely, a necessity given the height and weight of the towers. One notable construction method used for the Hermitage Plaza is the top-down construction technique. This involves building the above-ground structure while simultaneously excavating the basement levels. This approach allows for more efficient use of time and resources, ensuring that progress is made on all levels concurrently. The excavation was carried out using large diaphragm wall machines and hydrophrase technology, which help in digging deep and precise trenches filled with reinforced concrete. The core of each tower was constructed using a slip-form method, a continuous pouring of concrete that allows the core walls to rise steadily. This method not only speeds up the construction process, but also ensures the structural integrity of the towers. The slip-forming process involved around-the-clock operations, with teams working in shifts to maintain a continuous pour of concrete. The tower's steel framework was another critical aspect, requiring precision engineering and coordination. Large steel beams, prefabricated off-site, were transported to the site and lifted into place using high-capacity cranes. These beams form the skeleton of the towers, supporting the glass facade and internal floors. A significant challenge was the installation of the glass curtain wall, designed for energy efficiency and aesthetic appeal. Each glass panel was custom-made to fit the unique curvature and angles of the towers. Installation required specialized machinery and skilled labor to ensure each panel was correctly aligned and sealed to prevent leaks and improve thermal insulation. Wind tunnel testing was conducted to analyze the impact of wind loads on the towers. Based on these studies, engineers implemented tuned mass dampers within the structures. These devices counteract the swaying motion caused by high winds, providing stability and comfort for the building's occupants. The Rome Metro Line C extension is an ambitious project aimed at expanding Rome's metro system to improve connectivity and reduce traffic congestion in the city. The extension adds several new stations and 11 miles of track to the existing line, stretching from central Rome to the suburbs. The project involves complex tunneling operations beneath the historic center of Rome, requiring careful excavation to avoid damaging ancient structures and archaeological sites. Tunnel boring machines equipped with state-of-the-art ground-penetrating radar are used to detect and navigate around sensitive areas. The construction also incorporates advanced engineering techniques, such as the use of precast tunnel segments to accelerate the build process and enhance structural integrity. One of the significant challenges is managing the excavation and removal of spoil in a densely populated urban area. This is addressed through a combination of conveyor systems and specialized transport vehicles to minimize disruption to daily city life. The new stations are designed with modern architectural elements, integrating seamlessly with Rome's historic aesthetics, while providing improved accessibility features like elevators and escalators. The project also includes upgrading the existing stations and infrastructure to accommodate the increased passenger capacity. Advanced safety systems, including fire detection and suppression, as well as real-time passenger information systems, are installed to enhance commuter experience. The extension also incorporates green building standards, ensuring energy-efficient station operations and reduced carbon footprints. Upon completion, the Metro Line C extension will significantly reduce travel times, improve urban mobility, and contribute to the reduction of air pollution by encouraging the use of public transportation. The project is expected to transform the commuting experience in Rome, making it more efficient and reliable, and enhancing the overall quality of life for residents and visitors alike. The extension will also support the city's economic development by improving access to key commercial and cultural districts.
We move over to Canada to explain one of the most ambitious public transport projects, the Réseau Express Metropolitan. This automated light rail network aims to enhance connectivity across the greater Montreal area, spanning 41 miles with 26 stations. Constructing of the REM bridge began in 2018, with the project divided into several phases to manage the scale of the undertaking. With an estimated cost of $5 billion, the project is designed to operate both underground and above ground, requiring a variety of construction techniques. The sections of the REM that run underground involve tunneling through Montreal's complex geology. Tunnel boring machines are being used for these sections, with precision engineering required to avoid impacting existing underground infrastructure. For the elevated sections, engineers have employed precast concrete segments to construct the elevated guideways. Each segment is meticulously designed to interlock with the next, forming a continuous and robust structure capable of supporting the automated trains. The REM system is powered by a third rail, which provides a continuous supply of electricity to the trains. The choice of a third rail system, as opposed to overhead catenary lines, was made to reduce visual clutter and maintenance requirements. Additionally, the trains themselves are fully automated and driverless, equipped with the latest in signaling technology to ensure smooth operation. One of the most complex parts of the project is the Mount Royal Tunnel that was originally built for the Canadian Northern Railway in the 20th century. The tunnel is being repurposed and expanded to accommodate the REM trains, requiring extensive structural reinforcement. Another engineering aspect of the REM is its integration with Montreal's existing infrastructure. The REM will connect with Montreal Metro at several key stations, allowing for easy transfer between the systems. This integration extends to fare systems too, with plans for a unified fare structure that simplifies travel across different modes of transportation.
Next up, it's time to have a look at the world-famous One World Trade Center. Also known as the Freedom Tower, it stands as an indomitable pillar in the New York skyline at a patriotic height of 541 meters, including its spire. This makes it the tallest building in the Western Hemisphere, surpassing the Willis Tower in Chicago by 124 meters. Its 104 stories are encased in a shimmering facade of 2,000 pieces of prismatic glass, designed to reflect the sky and refract light, representing hope and endurance. One World Trade Center's design incorporates a reinforced concrete base, clad in blast-resistant materials, spanning 57 meters high, which is unprecedented in scale for such safety features. Above this base, office floors begin, featuring floor-to-ceiling windows that offer unobstructed views of Manhattan. The building's total floor area spans 3.5 million square feet, accommodating businesses, restaurants, and broadcast facilities. Its observation deck, located on the 100th to 102nd floors, provides visitors with breathtaking 360-degree views of New York City. But we have to talk about the Roche Tower too in Switzerland. The project involves the construction of a 205-meter-tall tower, which will house offices, research facilities, and conference spaces. Construction of the Roche Tower 2 began in 2018 and was finished in 2022. The foundation work for Roche Tower 2 required extensive excavation to accommodate the building's massive weight. Deep foundations were established using reinforced concrete piles driven into the ground, ensuring stability and load-bearing capacity. This phase involved careful geotechnical analysis to account for Basel's soil conditions and to mitigate any potential settling issues. One of the unique construction techniques used was the top-down construction method. This involved simultaneous construction of the above-ground structure and the underground basements. The top-down approach allowed for faster progress and reduced the overall construction timeline. Large steel columns were installed first, followed by the construction of the ground-level slab. As the above-ground floors were built upwards, the underground levels were excavated and constructed downwards. The core of the tower was constructed using a slip-form method, which allows for continuous pouring of concrete. This technique ensures a seamless and strong core structure, essential for the building's stability and integrity. Slip forming involved 24/7 operations, with teams working in shifts to maintain a continuous concrete pour. The steel framework for the tower required meticulous planning and coordination. Prefabricated steel beams and columns were transported to the site and assembled using high-capacity cranes. The use of building information modeling technology was crucial during this phase, allowing for precise planning and reducing the likelihood of errors. Installing the glass facade was a complex and precise process. Each glass panel was custom-made to fit the tower's design specifications, providing thermal insulation and energy efficiency. Specialized lifting equipment was used to hoist the large glass panels into place, where they were secured and sealed. Staying in Europe, we traveled to Paris for the world-famous Eiffel Tower megaproject. When completed in 1889 for the Exposition Universelle, it was the tallest man-made structure in the world, standing at 324 meters high. Constructed from 7,300 metric tons of iron, The Eiffel Tower comprises 1838 individual metal parts, joined together by 2.5 million rivets. This engineering marvel was designed by Gustave Eiffel, whose firm specialized in constructing bridges. Remarkably, the Eiffel Tower was intended to be dismantled in 1909, but was spared due to its utility as a radio telegraph station. Today, it attracts more than 7 million visitors annually, making it the most visited paid monument in the world. The tower's 3 levels are accessible to visitors, with restaurants on the first and second levels and the highest observation deck accessible at 276 meters. Each of the Eiffel Tower's 4 pillars rests on slabs of limestone with foundations sinking down to depths of about 7 to 15 meters, an architectural necessity that supports the massive iron lattice structure. The Eiffel Tower's iconic silhouette has inspired numerous replicas worldwide, but none match the original's architectural elegance and historical significance. The Cameron LNG project in the United States is a major liquefied natural gas export facility located in Hackberry, Louisiana. This $10 billion project involves the construction of 3 liquefaction trains, each capable of producing 4 million tons of liquefied natural gas per year. The construction includes the installation of advanced liquefied natural gas processing equipment, storage tanks, and extensive pipeline infrastructure to transport natural gas to the facility. One of the primary challenges is ensuring the safety and efficiency of the liquefaction process, which involves cooling natural gas to -260 degrees Fahrenheit. Advanced cryogenic technologies and safety systems are employed to manage the extreme temperatures and pressures involved. The project also includes the construction of a marine terminal with loading facilities to accommodate liquefied natural gas carriers. Extensive environmental assessments and mitigation measures are implemented to minimize the impact on local ecosystems and communities. Once completed, the Cameron Liquefied Natural Gas Project will significantly increase the United States liquefied natural gas export capacity, contributing to global energy security and economic growth. The project is expected to generate substantial economic benefits, including job creation and increased investments in the local economy. The Cameron Liquefied Natural Gas Project highlights the United States' growing role as a major exporter of liquefied natural gas and its contribution to global energy markets. The construction process employs specialized machinery such as cryogenic storage tank fabrication units, high-capacity pipeline construction equipment, and advanced safety monitoring systems to ensure the safe and efficient development of the liquefied natural gas facility.
Let's investigate the Bogota Metro project next, which is located in Colombia. The first line of this metro development, costing approximately $4.3 billion, will stretch over 24 kilometers and include 16 stations, serving millions of residents in Bogota. Construction of the Bogota Metro began in 2020, with the project expected to be completed by 2028. One of the primary challenges of this project is the dense urban environment in which it began to be constructed. To minimize disruptions to the city, much of the metro line is being built underground, requiring extensive tunneling and excavation work. The use of tunnel boring machines is essential for this task, as they can efficiently and safely excavate the tunnels while minimizing surface disruptions. The metro line is designed to accommodate high-capacity trains that can transport up to 72,000 passengers per hour. One of the innovative aspects of the metro project is the integration of advanced signaling and control systems. The metro will use a communication-based train control system, which allows for real-time monitoring and control of train movements. The construction of the metro also involves significant coordination with existing infrastructure and utilities. Engineers must carefully plan and execute the tunneling and excavation work to avoid disrupting critical services such as water, electricity, and telecommunications. This requires detailed mapping and analysis of the underground environment, as well as the use of advanced construction techniques to ensure the stability and integrity of the surrounding infrastructure. The Bogota Metro is expected to have a transformative impact on the city's transportation system. By providing a reliable and efficient alternative to road transport, the metro will help reduce traffic congestion and travel times for commuters.
It's time to travel to South Korea next. Rising majestically above Seoul, the Lotte World Tower stands as a pinnacle of architectural innovation and the tallest skyscraper in South Korea at 555 meters. Surpassing the One World Trade Center by 14 meters, it is ranked as the 5th tallest building globally. Designed to withstand the challenges of extreme weather, Lotte World Tower features a sleek, tapered design that minimizes wind pressure, a necessity in its lofty position above the bustling city. The structure is built with over 2,800 cubic meters of concrete and supported by a weighty 430,000 tons of steel, amounting to more than the iron used in the Eiffel Tower. Lot World Tower also features the world's fastest double-decker elevators, known as Sky Shuttle, which can travel from the ground floor to the 121st floor in 1 minute, reaching speeds of 600 meters per minute.
It's time to travel to Mexico City for the Torre Reforma mega project. Standing at 807 feet or 256 meters, it is the tallest building in Mexico. The tower's structural design was heavily influenced by the seismic activity prevalent in Mexico City. The triangular shape minimizes the surface area exposed to wind and seismic forces, distributing stress more evenly across the structure. The building's main structural system is composed of two massive reinforced concrete walls that run the full height of the tower. The walls are 4 feet thick at the base and taper as they rise, providing the necessary rigidity to resist lateral forces from earthquakes. These walls are connected by a series of concrete beams and steel braces, forming a robust structural core that anchors the building. But an even more innovative feature of Torre Reforma is its use of a diagrid system. This allows the tower itself to support itself without the need for internal columns, which maximizes the usable floor space. The diagrid structure is both lightweight and strong, capable of bearing the building's load while providing flexibility. During construction, engineers faced the challenge of Mexico City's soft and compressible subsoil, which is prone to subsidence and differential settlement. To address this, the foundation of Torre Reforma consists of 252 concrete piles, each driven 197 feet into the ground to reach a stable layer of clay and volcanic rock. These piles support a thick, reinforced concrete mat that distributes the load of the building evenly and prevents uneven settling. The building features a double-skin facade system that enhances its energy efficiency. The outer layer is composed of a glass curtain wall with operable windows, while the inner layer consists of concrete panels with narrow vertical slits. The concrete panels also provide thermal mass, helping to regulate indoor temperatures by absorbing heat during the day and releasing it at night.
It's time to travel to the United States for the tallest mast on planet Earth. The KVLY-TV Mast, towering at 629 meters, stands as the tallest structure in the Western Hemisphere and the tallest guide mast in the world. Erected in 1963 near Blanchard, North Dakota, this engineering feat surpasses the height of other monumental structures like Tokyo Skytree and Shanghai Tower when considering guide masts alone. Engineered to enhance broadcast range, the mast extends television coverage across the eastern North Dakota and northwestern Minnesota plains. It utilizes approximately 30 kilometers of guy wires, which are anchored in 3 directions to stabilize the structure against the formidable winds typical of the Great Plains. Constructed with high-strength steel, the mast weighs around 9,000 pounds at its pinnacle, despite its towering presence. The mast foundation is embedded deeply into the earth, ensuring structural integrity and resistance to torsional forces caused by harsh weather. Visibility of the mast from great distances requires aviation safety measures, including numerous red warning lights along its length to alert aircraft. It's time to investigate the Pont de Saint-Nazaire in France, which is a major infrastructure project focused on improving transport connectivity across the Loire River. Construction of this new cable-stayed bridge began in 2015, with completion achieved in 2023. The project, estimated at around $600 million, aims to replace the existing bridge and handle increasing traffic volumes. To begin, extensive foundation work was required to support the new bridge's structure. Engineers used deep drilling techniques to install large-diameter piles deep into the riverbed, ensuring stability and load-bearing capacity. These piles were constructed using reinforced concrete, capable of withstanding the considerable weight and dynamic forces exerted by the bridge and traffic. The bridge features a main span of 404 meters, making it one of the longest cable-stayed bridges in France. Construction involved assembling massive steel girders and precast concrete segments, which were transported to the site and lifted into place using high-capacity cranes. The precision alignment of these segments was critical to ensure the structural integrity and smooth curvature of the bridge. Cable installation was another key phase. The stay cables, made of high-strength steel, were anchored to the bridge deck and pylons. Tensioning these cables required meticulous calibration to balance the load distribution across the bridge. Engineers used hydraulic jacks to apply the necessary tension, carefully monitoring the stresses to prevent any structural imbalances. Managing construction activities while maintaining traffic flow on the existing bridge posed a significant challenge. To minimize disruption, a phased construction approach was implemented. Sections of the new bridge were completed and opened to traffic in stages, allowing continuous use of the old bridge until the new one was fully operational. This approach demanded precise scheduling and coordination to ensure safety and efficiency. The construction of the Pont de Saint-Nazaire exemplifies modern engineering and construction techniques, blending innovative methods with sustainable practices. The North Offshore Wind Farm in the Netherlands is a major renewable energy project designed to harness the power of the North Sea. This offshore wind farm, consisting of 150 turbines, is set to generate 1.2 gigawatts of electricity, enough to power over 1 million homes. The construction involves the installation of massive wind turbines, each standing over 650 feet tall, mounted on monopile foundations driven deep into the seabed. One of the primary challenges is the harsh marine environment, including strong winds and waves, which necessitate the use of advanced engineering techniques and durable materials. Specialized installation vessels and cranes are used to transport and erect the turbines. The project also includes the construction of an offshore substation and extensive underwater cabling to connect the generated power to the onshore grid. Environmental assessments and mitigation measures are implemented to minimize the impact on marine life and ecosystems. Once completed, the North Offshore Wind Farm will significantly contribute to the Netherlands' renewable energy capacity, reducing carbon emissions and promoting sustainable energy development. The project represents a significant step towards meeting the country's renewable energy targets and reducing dependence on fossil fuels. The wind farm is expected to generate substantial economic benefits, including job creation and increased investments in the local economy. The project also highlights the Netherlands' leadership in renewable energy and offshore wind technology, setting an example for other countries to follow. The construction process employs advanced machinery such as specialized installation vessels, high-capacity cranes, and underwater cable-laying equipment to ensure the precise and efficient assembly of the wind turbines and associated infrastructure.
It's time to travel over to the United States for the Gilmerton Bridge Replacement Megaproject. The new bridge, costing approximately $134 million, aims to improve traffic flow and safety for the thousands of vehicles and vessels that pass through this corridor daily. Construction of the Gilmerton Bridge replacement began in 2009, with the new bridge opening to traffic in 2013. The new bridge is a vertical lift bridge, which provides several advantages over the old bascule bridge. The vertical lift design allows for a higher clearance for maritime traffic, reducing the number of bridge openings and minimizing delays for both road and river traffic. The new bridge features a vertical clearance of 35 feet when closed and up to 135 feet when fully lifted, accommodating larger vessels that navigate the river. The construction of the bridge includes several advanced engineering techniques. The bridge's foundations were constructed using drilled shafts, which provide greater stability and load-bearing capacity compared to traditional pile foundations. These shafts were drilled deep into the riverbed, and the bridge could support the heavy traffic loads and withstand the harsh environmental conditions of the river. One of the key innovations in the Gilmerton Bridge replacement project was the use of precast concrete segments for the bridge's superstructure. These segments were manufactured off-site and transported to the construction site, where they were assembled using a balanced cantilever method. The project also included significant upgrades to the bridge's mechanical and electrical systems. The new bridge is equipped with state-of-the-art lifting machinery and control systems, ensuring reliable and efficient operation. The project included the construction of new pedestrian and bicycle pathways, enhancing accessibility and promoting alternative methods of transportation. Let's travel over to the Netherlands next to talk about one of the biggest stations in Europe. Rotterdam Central Station is a key transportation hub, and its recent redevelopment has been a significant engineering accomplishment. The project, completed in 2014, transformed the station into a modern structure, handling over 110,000 passengers daily and integrating high-speed rail services with local and regional transit systems. The construction of the new station was complex, given its location at the heart of the bustling city. The station's redevelopment required extensive planning and execution to minimize disruptions to the ongoing operations of trains, buses and trams, while also accommodating the heavy pedestrian traffic typical of a central transit hub. The station's redesign included the construction of a large roof structure that covers the platforms in the main hall. This roof is supported by a series of steel trusses that span significant distances without intermediate supports, creating an open and spacious environment. The roof spans approximately 250 meters in length and 150 meters in width, and its construction required the use of over 6,000 tons of steel. The steel trusses were prefabricated off-site and then transported to the construction site where they were lifted into place using large cranes. The precision required in aligning and connecting these trusses was significant, given the scale and the need to ensure structural integrity across such a vast expanse. In addition to the roof, the station's platforms and tracks were completely overhauled. This involved the installation of new track systems, including the complex network of switches and crossings required to manage the flow of high-speed trains. Underground, the station's foundations were reinforced to support the new structures above. This included the construction of deep foundation piles driven deep into the ground to stabilize the station and ensure it could support the weight of the new roof. The foundations also had to accommodate the construction of new underground passageways and facilities, which were essential for improving passenger flow. The station had to connect seamlessly with existing tram and bus services, as well as provide access to the city's metro system. This required the construction of new tunnels and passages, as well as the modifications of existing structures to ensure they could handle the increased loads.
It's time to travel to the seas now for the Troll, a platform located in the North Sea. At 472 meters tall, it is not only the tallest structure ever moved by mankind, but also surpasses the Petronas Twin Towers in height. This gas production platform is primarily stationed in the Troll gas field, about 80 kilometers northwest of Bergen, Norway. Constructed with prodigious dimensions, Troll A's total weight is over 1.2 million tons, including ballast, a mass greater than the heaviest man-made objects ever moved. The platform's legs are each 1.2 meters in diameter, extending 303 meters below the sea level into the seabed. Commissioned by Statoil, the platform began operations in 1996. Remarkably, it features accommodation to house up to 200 workers who manage its daily operations. The deck carries all the equipment necessary for drilling and gas extraction, arranged to maximize efficiency and safety. The platform's elevation above the water is 369 meters, which is taller than the Eiffel Tower, providing a stark perspective on its monumental scale. Troll A is also equipped with cutting-edge technology to handle daily gas production of about 83 million cubic meters, the high efficiency of which underscores Norway's leading role in the global energy sector. Let's travel over to Germany now, where the Kohlbrand Bridge is undergoing a major infrastructure project aimed at replacing the existing bridge. The new bridge will connect the port of Hamburg with the city's road network, providing a critical transport link. Construction of the new Kohlbrand Bridge began in 2020, with completion expected by 2025. The project represents a substantial investment, estimated at around $1.5 billion. The new bridge will feature a main span of 325 meters, making it one of the longest cable-stayed bridges in Germany. The foundation work for the Kohlbrand Bridge required extensive geotechnical analysis to determine the optimal locations for the deep piles. Large diameter piles were driven deep into the riverbed to provide the necessary support for the bridge's massive structure. These piles were made of reinforced concrete, designed to withstand the substantial loads and dynamic forces exerted by the bridge and traffic. One notable construction technique used in the project is the incremental launching method for the bridge deck. This method involves constructing the bridge deck in sections on the shore, and then incrementally launching these sections over the piers using hydraulic jacks. This technique reduces the need for extensive scaffolding and minimizes the environmental impact on the river. The precise alignment and connection of each deck section required meticulous planning and execution. The bridge's cable-stayed design features high-strength steel cables anchored to the bridge deck and pylons. Installing these cables involved using specialized cranes and tensioning equipment to ensure the correct load distribution. The pylons, constructed using slip-forming techniques, rise majestically above the river, providing both structural support and aesthetic appeal. Managing construction activities while maintaining traffic flow on the existing bridge posed a significant challenge. To minimize disruption, the project team implemented a phased construction approach. Sections of the new bridge were completed and opened to traffic in stages, allowing continuous use of the old bridge until the new one was fully operational. The construction of the Kohlbrand Bridge exemplifies modern engineering and construction techniques, blending innovative methods with sustainable practices. The Ningbo-Zhoushan Port expansion in China is a massive infrastructure project aimed at enhancing the capacity and efficiency of one of the world's busiest ports. The expansion includes the construction of new deep-water berths, container terminals, and logistics facilities to accommodate the growing volume of international trade. One of the primary challenges is the dredging and land reclamation required to create the new berths and terminals. Advanced dredging techniques and equipment are employed to ensure precision and minimize environmental impact. The project also involves the construction of state-of-the-art port infrastructure, including automated container handling systems, advanced logistics facilities, and modern navigation aids. To improve connectivity, extensive road and rail networks are being developed to link the port with major industrial and commercial centers. The expansion also incorporates sustainable practices, such as energy-efficient systems and renewable energy sources, to reduce the port's environmental footprint. Once completed, the Ningbo-Zhoushan Port expansion will enhance China's position as a global trade hub, boosting economic growth and facilitating international commerce. The project is expected to significantly increase the port's capacity, allowing it to handle larger vessels and more cargo efficiently. The expansion will also create job opportunities and stimulate economic development in the surrounding regions, contributing to China's overall economic growth. The construction process utilizes advanced port machinery such as automated stacking cranes, high-capacity dredgers, and specialized container handling equipment to ensure efficient and precise development of the new port facilities.
Next up, we travel over to the country of Nigeria to talk about the Third Mainland Bridge. Originally opened in 1990, the Third Mainland Bridge spans 11.8 kilometers and is the longest of 3 bridges connecting Lagos Island to the mainland. The expansion and rehabilitation project, costing approximately $300 million, focuses on addressing structural wear and improving traffic flow in one of Africa's most populous cities. Construction commenced in 2018 with a focus on repairing the bridge's deteriorating sections and enhancing its structural integrity. One of the primary engineering challenges was the need to work on a live bridge that supports over 100,000 vehicles daily. To minimize disruptions, the project was executed in phases with specific sections of the bridge closed for repair while traffic was rerouted to alternate routes. This required precise planning and coordination to ensure safety and efficiency. The rehabilitation work involved several advanced engineering techniques. Structural assessments revealed issues with the bridge's expansion joints, bearings, and docking. To address these, engineers employed high-pressure water jets to remove deteriorated concrete and replaced it with high-performance materials that offer greater durability. The expansion joints, critical for accommodating thermal expansion and contraction, were replaced with modern flexible joints designed to withstand heavy traffic loads and environmental conditions. In addition to structural repairs, the project included the installation of new asphalt overlays to improve the road's surface. This involved milling the existing surface to create a suitable base for the new asphalt layers. Engineers use state-of-the-art paving machines to ensure smooth and even surfaces, essential for enhancing driving comfort and reducing wear and tear on vehicles. One of the innovative solutions employed in the project was the use of underwater drones to inspect and repair the bridge's underwater supports. These drones, equipped with high-definition cameras and sonar technology, provided detailed images and data on the condition of the submerged structures. The successful completion of the Third Mainland Bridge expansion is expected to significantly improve traffic flow and safety in Lagos, reducing congestion and travel times for commuters.
Let's travel to Russia next to inspect the Ostankino Tower, located in Moscow. Completed in 1967 during the Soviet era at a height of 540 meters, the Ostankino Tower was designed primarily for telecommunications and to mark the 50th anniversary of the October Revolution. It holds the distinction of being the first structure outside the United States to exceed 500 meters in height. The tower's construction incorporates over 55,000 cubic meters of concrete and 3,000 tons of steel, a testament to Soviet engineering prowess. Ostankino's antenna allows for broadcasting television and radio signals across a 1,000-kilometer radius, covering an immense swath of Russia's populace. It is equipped with multiple observation decks and a revolving restaurant, offering panoramic views of Moscow, making it a significant cultural and tourist attraction. The tower's fire in 2000 led to extensive renovations, including the installation of advanced fire safety systems, ensuring its resilience and safety for future generations. Ostankino's unique lattice structure is not only functional, but also iconic, designed to withstand severe Russian weather conditions and seismic activity. Let's move over to the Netherlands next for the highly impressive North-South Line Metro project. The new metro line, which runs from the northern to the southern parts of Amsterdam, provides a fast and efficient transport option for residents and visitors. The project involved the construction of new tunnels, stations, and tracks, significantly enhancing the city's transport network. Construction of the North-South Line began in 2002, with completion achieved in 2018. The project represents a substantial investment, estimated at around $3.1 billion. One of the primary challenges of the project was tunneling through the soft and waterlogged soil of Amsterdam, which required advanced engineering techniques and machinery. The North-South Line features 9 new stations, each designed with modern amenities and advanced technology. Sustainability is a key focus of the North-South Line project. The new metro line is powered by renewable energy, and the stations are equipped with energy-efficient systems, such as LED lighting and advanced heating and cooling technologies. One of the significant challenges of the project was maintaining the city's normal operations while construction was underway. To minimize disruption, the project team employed a phased construction approach, allowing sections of the metro line to be completed and open to the public, while work continued on other sections. This approach requires careful planning and coordination to ensure that the project stays on schedule and within budget. The North-South Line has significantly improved public transport in Amsterdam, providing a fast and reliable connection between the northern and southern parts of the city. The new metro line has reduced travel times and eased congestion on other transport routes, contributing to the overall development of the city's transport network.
We don't have to travel far for the next construction project. Rogers Place in Edmonton, Alberta, is a multi-purpose arena and the home of the NHL's Edmonton Oilers. The structure of Rogers Place spans over 1 million square feet and seats approximately 18,500 for hockey games, expandable to 21,000 for concerts. One of the most striking features of the building is its sweeping curved roof, which was designed to evoke the undulating landscape of Alberta. The roof is supported by a series of long-span trusses, the largest of which spans 531 feet and weighs approximately 1,000 tons. These trusses were prefabricated and then assembled on-site, requiring the use of large cranes capable of lifting and positioning the massive steel components. The interior of the roof is lined with sound-absorbing materials to enhance acoustics for concerts and events, while the roof's insulation helps maintain the temperature inside, crucial for maintaining the ice surface for hockey games. Beneath the surface, Rogers Place features a complex foundation system designed to handle the load of the massive structure. The arena is built on a combination of deep foundations, including over 1,200 piles driven deep into the ground to support the building's weight. These piles are connected by a concrete grade beams and a thick slab on grade, providing a stable base for the arena's superstructure. The construction was tightly confined, with limited space for staging and assembly. To address this, the construction team employed just-in-time delivery of materials and used tower cranes strategically placed around the site to lift and position building components with precision. The facade features large sweeping panels of glass that offer views of the downtown skyline. The curtain wall system used for the facade is designed to withstand Edmonton's harsh climate, providing excellent thermal performance. Rogers Place also features the largest true high-definition scoreboard in the NHL, measuring 46 feet wide and 36 feet high.
Staying in Asia, let's move over to China for an extremely tall dam. The Baihetan Dam, located on the Jinsha River, is one of the most formidable hydroelectric power stations in the world. At a height of 289 meters, it is taller than the Eiffel Tower. This arched dam has the capacity to produce a massive 16,000 megawatts of power through its 16 turbines. Designed for more than just power generation, Baihetan also plays a crucial role in flood control, irrigation, and river navigation enhancement. It creates a reservoir that holds 20.6 billion cubic meters of water, almost double the volume of Lake Mead, the largest reservoir in the United States. Upon completion, Baihetan Dam has significantly bolstered China's renewable energy portfolio, aligning with the country's ambitious goals to reduce reliance on coal and cut carbon emissions. It serves as a critical element in China's West-East power transmission strategy, which aims to supply the eastern regions with clean, renewable energy generated from the western provinces. The Dolra Solar Park in India is one of the world's largest solar energy projects, designed to generate 5 gigawatts of electricity. Located in the Dolra Special Investment Region in Gujarat, this solar park covers over 27,000 acres. The project involves the installation of millions of photovoltaic panels, advanced inverters, and extensive transmission infrastructure to connect the generated power to the grid. One of the major challenges is the harsh environmental conditions, including high temperatures and dust, which necessitate the use of durable and efficient solar technologies. To address this, the project employs bifacial solar panels, which can capture sunlight on both sides, and robotic cleaning systems to maintain panel efficiency. The solar park also includes energy storage solutions, such as large-scale battery systems, to ensure a stable supply of electricity. The construction involves a modular approach, allowing for phased development and scalability. Extensive environmental assessments are conducted to minimize impacts on the local ecosystem, including measures to protect wildlife and manage water resources sustainably. The project is designed to integrate seamlessly with the existing grid infrastructure, ensuring reliable power delivery. Once completed, the Dolra Solar Park will significantly contribute to India's renewable energy capacity, reducing carbon emissions and promoting sustainable development. The project will also provide a boost to the local economy by creating jobs and fostering the growth of a clean energy industry in the region. By harnessing solar energy, the Dolra Solar Park sets a precedent for future renewable energy projects, showcasing India's commitment to sustainable development. The project is expected to attract further investments in renewable energy, positioning India as a global leader in the clean energy sector. The solar park will also serve as a model for large-scale solar energy projects worldwide, demonstrating the potential of renewable energy to meet the growing energy demands sustainably. The construction process utilizes advanced machinery such as solar panel mounting systems, high-capacity cranes, and automated assembly lines to ensure efficient and precise installation of the solar arrays.
But we haven't talked about the Maputo-Catembe Bridge yet, located in Mozambique. Construction of this bridge began in 2014 and was completed in 2018. One of the primary engineering challenges was constructing a bridge that can span the wide expanse of Maputo Bay while withstanding the region's environmental conditions. The bridge features a main span of 680 meters, supported by 2 massive towers that rise 137 meters above the water. The construction of the bridge's towers involved using high-strength concrete and reinforced steel. The towers were constructed using slip-form construction techniques, where concrete is continuously poured into a moving formwork that gradually climbs the structure. This method allows for more efficient and continuous construction of tall structures with consistent quality. The towers were designed to withstand strong winds and seismic activity, ensuring the bridge's stability and safety. The bridge's deck is suspended from the towers using large-diameter steel cables. These cables are made from high-strength steel and are capable of bearing significant loads. The cables were fabricated in sections, then transported to the construction site, where they were then assembled and installed using specialized cranes and cable-spanning techniques. The deck itself is composed of precast concrete segments, which were manufactured off-site and then transported and assembled on-site. The construction of the bridge's foundations involved significant geotechnical challenges. The foundations were constructed using large-diameter bored piles, which were drilled deep into the seabed to provide the necessary support for the bridge towers. The piles were reinforced with steel cages and filled with high-strength concrete to ensure their durability and load-bearing capacity. The construction process also included the installation of expansion joints and bearings to accommodate the bridge's movements due to thermal expansion, traffic loads, and seismic activity. The expansion joints are designed to allow for controlled movements of the bridge deck while maintaining a smooth and continuous driving surface.
At 553 meters, this icon was the undisputed tallest freestanding structure in the world from its completion in 1976 until 2007. Imagine standing atop the Skypod deck. At 447 meters, you're taking in views that stretch over 160 kilometers on a clear day. Designed to endure the fierce Canadian elements, it incorporates 40,500 cubic meters of concrete and over 4,500 tons of steel. This robust construction is designed to withstand wind speeds of up to 418 kilometers per hour and is equipped with a sophisticated lightning attraction system that handles around 75 lightning strikes per year. Function meets form with the tower's practical use as a key telecommunications hub for Toronto. It broadcasts radio and television services across the cityscape, proving that this landmark isn't just for show, it's an integral part of daily life in Toronto. The journey up can be as thrilling as the view. In one of 6 high-speed elevators, ascend at a rate of 22 kilometers per hour to the main pod, which features not only the glass floor, but also a revolving restaurant that offers a 360-degree sweep of the city below over a 72-minute rotation.
We have to investigate the George Massey Tunnel next, located in British Columbia, Canada. It's a significant engineering project that runs beneath the Fraser River, connecting the cities of Richmond and Delta. The tunnel spans 629 meters and consists of 4 lanes carrying traffic along British Columbia Highway 99. It was constructed using the immersed tube method, a technique that was innovative for its time and involved sinking prefabricated tunnel sections into a trench dredged along the riverbed. The construction process began with the dredging of a 10-meter deep trench in the riverbed where the tunnel sections would later be placed. These sections, made of reinforced concrete, were prefabricated on land and then floated out to the installation site. Each section was 344 feet long and weighed approximately 4,700 tons. Once floated into position, they were submerged into the trench using a controlled process of water ballasting, where water was pumped into the tanks within the tunnel sections to sink them slowly and precisely into place. After placement, the sections were connected underwater using watertight joints. The connections between sections were critical to ensuring the tunnel's integrity, as they had to be watertight. Once the tunnel sections were in place and connected, the trench was backfilled with gravel and rock to anchor the tunnel securely to the riverbed and protect it from potential damage. The interior of the tunnel was then lined with a secondary layer of concrete to provide a smooth driving finish. The tunnel was designed to handle up to 10,000 vehicles per day at its opening, but by 2013, traffic volumes had increased to over 80,000 vehicles daily. This significant increase in traffic over the decades has highlighted the need for infrastructure upgrades, leading to the ongoing discussions and planning for a replacement or expansion of the tunnel. In addition to its role in transportation, the tunnel also had to be engineered to withstand seismic activity, given Vancouver's location. While seismic considerations were not as advanced during the tunnel's original construction, retrofits and evaluations have been conducted over the years to enhance the tunnel's ability to withstand potential earthquakes.
Next up, it's time to travel over to Norway for the Oslo Central Station project. This development involves extensive upgrades to the station's infrastructure, including the construction of new platforms, tracks, and passenger facilities. The goal is to improve capacity, accessibility, and the overall passenger experience. Construction of the Oslo Central Station redevelopment began in 2018, and it's bound to be fully operational by the end of 2024. The project represents a significant investment, estimated at around $2 billion. One of the key features of the redevelopment is the expansion of the station's concourse, which will provide more space for passengers and reduce congestion during peak times. The project includes the construction of new platforms and tracks to accommodate the increasing number of trains and passengers using the station. Additionally, the redevelopment will feature new retail and dining options, creating a vibrant and dynamic environment for travelers. One of the primary challenges of the Oslo Central Station project has been maintaining station operations while construction is underway. To minimize disruption, the project team has implemented a phased construction approach, allowing sections of the station to remain open and functional throughout the redevelopment process. This approach has required careful planning and coordination to ensure that the project stays on schedule and within budget. The improved facilities and infrastructure will support the growing number of passengers using the station and contribute to the overall development of the city's transport network. Let's travel to the United States, where the Gateway Arch is located. At 192 meters or 630 feet, it is the tallest arch in the world and the tallest man-made monument in the Western Hemisphere. It was designed by Finnish-American architect Eero Saarinen in 1947 and completed in 1965. The arch's exterior is clad in stainless steel, making it the world's tallest stainless steel monument. This material choice not only contributes to its gleaming appearance, but also reflects its surroundings. Building the Gateway Arch was a feat of engineering, requiring the precise fabrication of 142 stainless steel sections. Moreover, the arch is hollow, containing a unique tram system that carries visitors to an observation area at the top, offering sweeping views of St. Louis and the Mississippi River. Its construction cost approximately $13 million at the time, which is around $100 million today. The Hefei-Wuhan High-Speed Railway in China is a major infrastructure project aimed at enhancing connectivity between the cities of Hefei and Wuhan. This 300-mile high-speed rail line is designed to support train speeds of up to 220 miles per hour, reducing travel time between the two cities to just over 1 hour. The project involves the construction of multiple tunnels, bridges, and viaducts to navigate the complex terrain. One of the key engineering challenges is the construction of the long tunnels through mountainous regions, which requires advanced tunnel boring machines and precise engineering techniques. The railway line is equipped with state-of-the-art signaling and communication systems to ensure safety and efficiency. To minimize environmental impact, extensive environmental assessments and mitigation measures are implemented, including wildlife crossings and noise barriers. The project also includes the construction of modern stations equipped with advanced passenger amenities and accessibility features. The Hefei-Wuhan High-Speed Railway is part of China's broader efforts to expand its high-speed rail network, promoting economic development and regional integration. Once completed, the railway line will provide a fast, efficient, and environmentally friendly transportation option, boosting connectivity and economic growth in the region. The project is expected to significantly reduce carbon emissions by providing a greener alternative to air and road travel. The Hefei-Wuhan High-Speed Railway will not only improve travel efficiency, but also stimulate economic activities in the regions it connects, fostering greater regional cooperation and development. The railway is also expected to enhance tourism by making it easier for travelers to access the cultural and historical attractions in both cities, further contributing to the local economies. The construction of the railway employs high-speed rail technology, including the use of continuous welded rail, slab track systems, and automated track laying machines to ensure smooth and reliable train operations.
We have to talk about the Port of Dum next, which is located in Oman. This $10 billion project covers an area of 2,000 hectares and includes the construction of port facilities, industrial zones, and residential areas. Construction of the Port of Duke began in 2011, with the project expected to be completed by 2025. One of the primary challenges of this project is the remote location, which requires extensive infrastructure development to support the construction and operation of the port. This includes the construction of roads, utilities, and housing for workers, as well as the development of logistics and supply chain networks. The port facilities are designed to accommodate a wide range of vessels, including container ships, oil tankers, and bulk carriers. The construction of the port involves significant dredging and reclamation work to create deep water berths and turning basins. This requires the use of advanced dredging equipment and techniques to ensure the stability and safety of the port structures. Dredging operations at the Port of Duke utilize cutter suction dredgers and trailing suction hopper dredgers to excavate and transport sediment from the seabed. These dredgers are capable of handling various soil conditions, from soft silt to compacted sand and rock. The construction of the port quay walls and breakwaters involves significant engineering challenges. The quay walls are constructed using precast concrete blocks and steel sheet piles driven deep into the seabed. These structures provide the necessary strength and durability to withstand the forces exerted by large vessels and the harsh marine environment. The quay walls are built using a combination of precast concrete blocks and in-situ concrete casting. The precast blocks are manufactured off-site to ensure quality and consistency, then transported and installed using heavy-duty cranes. The sheet piles are driven into the seabed using hydraulic pile drivers, which provide the necessary force to penetrate the dense seabed material. But have you ever heard about the construction of the Amazon Spheres? Located in Seattle, the Spheres are part of Amazon's headquarters in the Denny Triangle neighborhood and consist of 3 interconnected glass domes, the largest of which measures 90 feet in height and 130 feet in diameter. The design and construction of the spheres involved significant engineering challenges, particularly in balancing the aesthetic and functional needs of the project. One key engineering feature is the use of steel framework composed of pentagonal hexacantahedron geometry, which consists of 60 sides and is derived from the shape of a Catalan salad. The steel frame comprises over 2,600 individual members, connected by nearly 650 unique nodes, each precisely fabricated and assembled to create the seamless shape of the domes. The assembly of the frame was conducted in phases, with sections of the steel framework lifted into place and bolted together before the glass panels were installed. The project uses approximately 2,643 panes of glass, each with a special low iron content to ensure maximum transparency. These panes were custom manufactured with a unique coating that allows for optimal light transmission while reducing glare and solar heat gain. To support the lush, diverse environment inside, the spheres are equipped with a sophisticated climate control system that maintains a temperature range of 68 to 72 degrees Fahrenheit. The climate control is managed by a combination of air handling units, radiant floor heating, and automated shading systems that respond to changing sunlight conditions throughout the day. The Amazon spheres feature a unique soil management system that supports diverse plant growth in a confined space. This system includes custom-designed planting beds, integrated irrigation and drainage, and a carefully controlled soil composition that mimics natural environments.
We have to move over to Finland next for the Hanhikivi-1 nuclear power plant. Located in Pyhäjoki, the project involves the construction of a new nuclear reactor, which will provide a stable and reliable source of electricity for the region. Construction of the Hanhikivi-1 nuclear power plant began in 2015, with completion expected by 2029. The project represents a substantial investment, estimated at around $7 billion. The plant will feature a Russian-designed Viver 1A200 reactor, which is known for its high safety standards and efficiency. The reactor will have a capacity of 1A200 megawatts, enough to power around 1 million homes. One of the primary challenges of the Hanhikivi-1 project has been ensuring compliance with Finland's stringent nuclear safety regulations. The project team has worked closely with regulatory authorities to ensure that the plant meets all safety requirements and is constructed to the highest standards. This includes rigorous testing and quality control measures throughout the construction process. The Hanhikivi-1 nuclear power plant will incorporate advanced safety features, such as a double containment structure, an emergency core cooling system, and a passive heat removal system. These features are designed to ensure the safety of the plant and its surrounding areas in the event of an emergency. The project also includes extensive environmental monitoring and mitigation measures to protect the local ecosystem. Nuclear power is a low-carbon energy source, and the plant will play a crucial role in helping Finland achieve its climate goals. By providing a reliable and stable source of electricity, the plant will reduce the country's dependence on fossil fuels and contribute to the reduction of greenhouse gas emissions. The construction of the Hanhikivi-1 nuclear power plant involves the use of advanced engineering and construction techniques. The project team has employed state-of-the-art technology to manage the complex logistics of building a nuclear power plant, including the transport and installation of large and heavy components. But the absolutely tallest structure on planet Earth is, of course, the Burj Khalifa, located in Dubai. Completed in 2010 at a height of 828 meters, the superstructure took more than 22 million man-hours to build. The tower features 163 floors above ground, including corporate suites, residences, and the Armani Hotel. It also boasts the highest observation deck in the world, located on the 148th floor at 555 meters, which offers breathtaking views of Dubai and the Persian Gulf. Hosting the world's second highest swimming pool on the 76th floor and the world's highest restaurant on the 122nd floor, the Burj Khalifa is not only a feat of engineering but also a luxury destination for global tourists. The project is also pivotal for technological innovations, such as the telescopic spire comprising more than 4,000 tons of structural steel. Given its height, the Burj Khalifa is designed to withstand Dubai's hot summer temperatures with its reflective glazing, and the exterior temperature at its top is significantly cooler than at its base. The Royal Gorge Bridge in the United States is undergoing a major renovation project to enhance its structural integrity and improve visitor experience. Spanning 1,260 feet across the Arkansas River in Colorado, the bridge is one of the highest suspension bridges in the world, towering 955 feet above the river. The renovation involves replacing the wooden deck with high-strength, weather-resistant materials to ensure durability and safety. Advanced construction techniques, such as the use of prefabricated components and modular assembly, are employed to minimize disruption to visitors and ensure precision. One of the primary challenges is maintaining the structural integrity of the historic bridge while incorporating modern materials and technologies. The project also includes the installation of new safety features, such as reinforced railings and automated monitoring systems to detect structural stresses. The renovation aims to preserve the bridge's historic character while enhancing its functionality and safety. Once completed, the Royal Gorge Bridge will continue to be a major tourist attraction, providing breathtaking views and a unique engineering marvel for visitors to enjoy. The renovation also includes improvements to the surrounding infrastructure, such as upgraded walkways and viewing platforms, enhancing the overall visitor experience. The project is expected to boost the local economy by attracting more tourists and providing new job opportunities in the tourism sector. The Royal Gorge Bridge renovation underscores the importance of preserving historic structures while adapting them to meet modern safety and usability standards. The construction process utilizes specialized machinery such as high-capacity cranes, prefabrication assembly lines, and automated monitoring systems to ensure the structural integrity and longevity of the bridge.
Let's move over to Egypt now, where the Grand Egyptian Museum is being constructed. Located near the pyramids of Giza, this $1 billion project covers approximately 120 acres and showcases Egypt's rich cultural heritage through state-of-the-art exhibits and facilities. One of the primary engineering challenges was creating a stable foundation for the massive structure, given the proximity to the pyramids and the potential for archaeological discoveries during excavation. Engineers employed advanced ground-penetrating radar and other non-invasive techniques to survey the site before construction, ensuring that any significant archaeological finds could be documented and preserved. The construction of the Grand Egyptian Museum involved several advanced engineering techniques. The building's foundations required deep excavation and the use of high-strength concrete to support the massive weight of the structure. To address the region's seismic activity, engineers incorporated earthquake-resistant features, such as base isolators and flexible joints, into the design. These features help absorb and dissipate seismic energy, protecting the structure from potential damage during an earthquake. One of the most striking features of the museum is the massive 82-ton statue of Ramses II, which stands in the entrance atrium. Engineers used a specially designed gantry crane and sophisticated system of rollers and supports to transport and position the statue without causing any damage. The sheer size of the project required the coordination of thousands of workers and the management of vast amounts of materials. Engineers employ advanced project management software to monitor progress, allocate resources, and address any issue that arose during construction.
Next up is Landmark 81, soaring majestically over Ho Chi Minh City, Vietnam. It reaches a towering height of 461 meters, making it the tallest building in Vietnam and among the top 20 tallest worldwide. The building consists of 81 floors and covers a floor area of 241,000 square meters, used for a mix of residential, retail, and leisure facilities, making it a multifunctional vertical city. Its design is inspired by the bamboo stalk, a symbol of traditional Vietnamese resilience and elegance. Landmark 81 boasts a luxury hotel, high-end apartments, and Vietnam's highest observatory deck, offering panoramic views of the city and the Saigon River. The development was completed in 2018 by the Vingroup conglomerate, with a design by the renowned architectural firm Atkins. The tower is part of a larger $1.5 billion Vinhomes Central Park development project, which aims to transform the city's skyline and elevate its international profile. Strategically positioned along the banks of the Saigon River, Landmark 81 is not only a commercial and residential hub, but also a beacon for eco-friendly practices, featuring vertical gardens and sustainable architecture elements.
Let's move over to San Francisco to cover the incredible construction process of Levi's Stadium. The project broke ground in April 2012, and the stadium was completed in just over 2 years. The total cost of construction was approximately $1.3 billion, with the stadium having a seating capacity of 69,000. The stadium structure is supported by a steel frame that weighs approximately 18,000 tons, providing the necessary strength to support the massive building while allowing the flexibility in the event of seismic activity. The seating bowl of Levi Stadium was designed with a steep pitch to bring fans closer to the action of the field. The project is one of the most technologically advanced sports venues in the world, with a robust network capable of supporting 40,000 concurrent connections. This required the installation of more than 400 miles of data cabling throughout the facility. The stadium includes parking for over 20,000 vehicles, with multiple access points designed to minimize congestion. The project's construction also focused on creating a multi-purpose venue, with the field being designed to be easily converted for soccer matches, concerts, and other events.
But what about the tallest clock tower in the world? Perched next to the Grand Mosque of Mecca, the Abraj Al Bait clock tower isn't just a skyscraper. It's a colossal marvel towering at 601 meters, making it one of the tallest and most striking man-made structures on Earth. Its clock face, the largest in the world, spans 43 meters in diameter, easily outclassing London's Big Ben by 5 times. Built at a staggering cost of $15 billion, this megastructure is part of a 7-tower complex that redefines luxury and scale. Above, a 93-meter-tall spire topped with a 23-meter golden crescent makes it a beacon visible from miles across the city, guiding pilgrims like a lighthouse of faith. With the world's largest floor area, the tower hosts an Islamic museum and a moon observation center, which provides astronomers and scholars a unique vantage point for sighting the moon, crucial for the Islamic calendar. Let's travel to Switzerland for the next project on our list, the Stade de la Tuileries. Located in the city of Lausanne, the stadium is part of a larger sports complex that includes training facilities, a sports academy, and recreational areas. The project aims to provide a modern and comfortable environment for athletes and spectators, enhancing the city's sports infrastructure. Construction of the Stade de la Tuileries began in 2018 and was completed in 2020. The project represents a significant investment, estimated at around $80 million. The stadium has a seating capacity of 12,000, with the possibility of expanding to 15,000 in the future. The design of the stadium emphasizes visibility and comfort, with unobstructed views from every seat and ample facilities for spectators. One of the unique features of the Stade de la Tuileries is its modular design, which allows for flexibility in its use and configuration. The stadium can be adapted to host a variety of events, including concerts, community events, and other sports competitions. This flexibility is achieved through the use of retractable seating and movable partitions, which can be adjusted to create different seating arrangements and field configurations. The stadium is equipped with advanced technology to enhance the spectator experience. This includes high-definition video screens, a state-of-the-art sound system, and extensive lighting to ensure excellent visibility for both day and night events. The Stade de la Tuileries has quickly become a landmark in Lausanne, providing a modern and versatile venue for sports and entertainment. The Xinjiang Solar Power Plant in China is one of the world's largest solar farms, covering over 30 square miles in the Gobi Desert. This massive renewable energy project is set to generate 2 gigawatts of electricity, enough to power around 1.5 million homes annually. The construction of the plant involves the installation of millions of photovoltaic panels, mounted on advanced tracking systems that follow the sun's path to maximize energy capture. Engineers have designed these systems to withstand the harsh desert environment, including extreme temperatures and high winds. One of the key challenges in this project is the logistics of transporting and installing such a vast number of solar panels and supporting structures in a remote location. To address this, the project employs a modular construction approach, allowing for efficient assembly and scalability. Additionally, innovative dust mitigation techniques are implemented to maintain panel efficiency, such as using anti-dust coatings and robotic cleaning systems. The plant is connected to the grid via high-voltage direct current transmission lines, which are capable of transmitting electricity over long distances with minimal losses. The project also incorporates energy storage solutions to ensure a stable supply of electricity, even during periods of low solar irradiance. These energy storage systems are crucial for balancing supply and demand, enhancing grid stability. This solar power plant represents a significant step towards reducing carbon emissions and promoting sustainable energy development in China. By harnessing the vast solar potential of the Gobi Desert, the project not only contributes to China's renewable energy targets, but also sets a benchmark for large-scale solar energy projects worldwide. The plant's success could pave the way for similar projects in other desert regions across the globe, demonstrating the viability of solar power as a major energy source. The project will also stimulate economic development in the region by creating jobs and providing a reliable energy source for local industries.
But what about the Cross River Rail project in Australia? This $5.4 billion project involves the construction of a 10.2-kilometer rail line, including a 5.9-kilometer twin tunnel under the Brisbane River in the city center. Construction of the Cross River Rail began in 2019, with the project expected to be completed by the end of 2024. One of the primary challenges of this project is the need to construct the tunnels beneath a densely populated urban area. To minimize disruption to the city, tunnel boring machines are used to excavate the tunnels. These machines can efficiently and safely bore through the ground while minimizing surface disruptions. The project also includes the construction of 4 new underground stations, which are designed to accommodate high-capacity trains and provide modern, accessible facilities for passengers. The project also involves significant upgrades to existing infrastructure, including track realignment and station enhancements. These upgrades are designed to improve the overall capacity and efficiency of Brisbane's rail network, providing a more reliable and convenient service for passengers. Environmental and social considerations are a key focus of the Cross River Rail project. Measures are being implemented to minimize the environmental impact of the construction and operation of the rail line. By providing a reliable and efficient alternative to road transport, the rail line will help reduce traffic congestion and travel times for commuters. In addition to the construction jobs, the operation and maintenance of the rail line will create long-term employment opportunities, further contributing to economic growth and development.
It's time to travel to Europe for one of the tallest wind turbines across the globe, called the NordLink wind turbine. Standing at a colossal height of 246 meters, this turbine is taller than most skyscrapers in Europe. Equipped with a rotor diameter of 220 meters, the NordLink wind turbine can generate up to 13 megawatts of power, enough to sustain approximately 20,000 homes. This makes it one of the most powerful turbines in operation today, dwarfing the average turbine, which typically provides between 2 to 3 megawatts. The NordLink's blade length is around 107 meters, each blade being almost as long as a football field. The turbine features cutting-edge technology that includes a lightning protection system, ensuring safety and operational continuity during the frequent thunderstorms common in northern Germany. The NordLink wind turbine contributes impressively to Germany's climate goals. By reducing the need for coal and gas, it prevents the emission of approximately 42,000 tons of CO2 annually. This clean energy generation is a critical step towards Germany's commitment to phasing out nuclear power by 2022 and coal by 2038. The Chenab Bridge in India is an engineering marvel, set to be the world's highest railway bridge upon completion. Spanning the Chenab River in the Himalayas, this bridge is part of the Udhampur-Srinagar-Baramulla rail link project, aiming to improve connectivity in the region. The bridge's arch design, stretching 1,315 feet across and rising 1,178 feet above the river, is a testament to advanced engineering and construction techniques. The construction involves the use of high-strength steel to withstand the challenging weather conditions and seismic activity in the region. One of the primary challenges is the erection of the massive arch, which is being done using a combination of cantilever and cable crane methods. Extensive wind tunnel testing and seismic analysis have been conducted to ensure the bridge's stability and safety. The project also includes the construction of approach roads, tunnels, and viaducts to connect the bridge to the existing rail network. Advanced construction methods, such as incremental launching and balanced cantilever construction, are employed to ensure precision and efficiency. The bridge is designed with multiple safety features, including automated monitoring systems to detect structural stresses and movements. Once completed, the Chenab Bridge will significantly reduce travel time, enhance trade and tourism, and provide a crucial link for the Indian railways in this remote and strategic region. The project also promises to boost the local economy by improving accessibility and creating jobs during the construction phase. The bridge will stand as a symbol of modern engineering prowess, attracting tourists and becoming a landmark in the region. Additionally, the improved rail connectivity is expected to facilitate the movement of goods and people, contributing to the economic development of the surrounding areas. The construction process itself has become a training ground for engineers, offering valuable experience in handling complex projects under challenging conditions. The construction of the Chenab Bridge employs specialized machinery such as cable cranes, hydraulic jacks, and high-precision surveying equipment to ensure accurate assembly and alignment of the bridge components.
Next up, we have to move over to Japan for the Azabudai Hills project, located in Tokyo. The project, costing approximately $5.5 billion, covers an area of 8.1 hectares and includes 3 skyscrapers, green spaces, and public facilities. Construction of Azabudai Hills began in 2019, with the project expected to be completed by the end of 2024. One of the primary challenges in this project is the dense urban environment in which it is being built. To minimize disruption to the surrounding area, construction is being carried out in phases, with careful planning and coordination to ensure safety and efficiency. The project features 3 high-rise buildings with the tallest reaching a height of 330 meters. These buildings will house offices, apartments, hotels, and retail spaces, creating a vibrant mixed-use environment. A key innovation in the Azabudai Hills project is the integration of green spaces and public facilities within the urban environment. The development includes a central park which covers approximately 24,000 square meters and provides a green oasis in the heart of the city. The project also incorporates state-of-the-art sustainability features such as energy-efficient building systems, renewable energy sources, and advanced waste management systems. One of the significant engineering challenges in the Azabudai Hills project is the construction of the underground infrastructure. This includes the creation of underground parking facilities, utility tunnels, and pedestrian networks that connects the various buildings and public spaces. Advanced tunneling and excavation techniques are used to ensure the stability and safety of the underground structures, while minimizing the impact of the surrounding environment. In addition to its architectural and environmental features, Azabudai Hills aims to create a sense of community and connectivity within the urban environment. The development includes a range of public amenities such as schools, healthcare facilities, and community centers, which are designed to meet the needs of residents.
Next up, we have to move over to the United Kingdom for the Liverpool Street Station redevelopment project. This endeavor is focused on enhancing capacity, improving accessibility, and upgrading facilities to meet the demands of increasing passenger numbers. The station, originally opened in 1874, is undergoing a significant overhaul to integrate contemporary design elements while preserving its historical character. A key feature of the redevelopment is the expansion of the station's concourse, which will increase the available space for passengers and reduce congestion during peak times. This includes the construction of new entrances, wider platforms, and additional escalators and lifts to improve the flow of people throughout the station. Sustainability is at the heart of the Liverpool Street Station redevelopment. The project includes the installation of energy-efficient lighting, water-saving fixtures, and a new waste management system designed to reduce the station's environmental footprint. The construction phase, which began in 2020, is scheduled to be completed by 2025. The redevelopment involves a substantial investment, estimated at around $1.5 billion. One of the difficult challenges of this project is maintaining station operations while construction is underway. To minimize disruption, the project team has implemented a phased construction approach, allowing sections of the station to remain open and functional throughout the redevelopment process. Another critical aspect of the redevelopment is the integration of Liverpool Street Station with the Elizabeth Line. This integration will provide seamless connections to other parts of London and improve travel times for commuters. The new concourse will connect directly to the Elizabeth Line platforms, enhancing accessibility and making it easier for passengers to navigate between different transport services.
It's time to talk about the Jakarta-Bandung high-speed rail in Indonesia, which is an ambitious project aimed at significantly reducing travel time between Jakarta and Bandung from over 3 hours to approximately 40 minutes. With an estimated cost of $6 billion, this project is Indonesia's first high-speed rail venture. Construction began in 2016, focused on advanced construction techniques and technologies. One of the primary engineering challenges was the diverse terrain between Jakarta and Bandung, necessitating the construction of numerous bridges and tunnels. The line features 13 tunnels, including the Walini Tunnel, the longest at 4.5 kilometers. The construction of these tunnels employed tunnel boring machines, essential for efficiently and safely excavating through varied geological conditions. The rail line is designed to accommodate speeds of up to 250 kilometers per hour, requiring the use of high-strength materials and precision engineering to ensure safety and stability. The tracks are laid on a slab track system, which provides greater durability and requires less maintenance compared to traditional ballast tracks. This system involves laying the rails on concrete slabs to fix in place with high-precision techniques to maintain the alignment and smoothness required for high-speed travel. A significant challenge faced during the construction was minimizing the impact on densely populated areas along the route. To address this, elevated tracks and viaducts were constructed in several sections, reducing the need for land acquisition and minimizing disruptions to local communities. Another critical aspect of the construction process was ensuring the rail line's resilience to seismic activity. Indonesia is located in a seismically active region, so the design incorporates earthquake-resistant features. These include flexible track systems and shock-absorbing materials that can withstand significant ground movement without compromising the rail line's integrity. Logistics played a crucial role in the project's success, given the scale and complexity of the construction. Materials and equipment had to be transported to various construction sites along the 142.3-kilometer route. This required a well-coordinated supply chain and efficient transportation network to ensure timely delivery and minimize delays.
Let's go to Germany for the Edge East Side Tower, located in the city of Berlin. Rising to an impressive height of 140 meters, this 35-story skyscraper will serve as a mixed-use facility with both office spaces and commercial areas. One of the unique aspects of the Edge East Side Tower is its integration of cutting-edge technology to create a smart and sustainable building. The tower will feature advanced energy management systems, including solar panels integrated into the facade and smart lighting systems that adjust based on natural light availability. These systems are expected to reduce the building's energy consumption significantly, setting a new standard for green buildings in Germany. Construction of the Edge East Side Tower began in 2020, and it was completed in 2023. The project involves a substantial investment, estimated at around $400 million. The construction site is strategically located near the Warschauer Strasse station, making it easily accessible by public transport. The lobby features a spacious atrium with green walls and seating areas, providing a welcoming environment for visitors. Challenges during construction have included coordinating the installation of the advanced energy systems and ensuring that the building meets stringent sustainability criteria. The project team has employed innovative construction techniques to streamline the process, such as prefabricated components and modular construction methods. Standing at a commanding height of 328 meters, the Sky Tower in Auckland is not only the tallest freestanding structure in the Southern Hemisphere, but also an engineering and telecommunications beacon. Its height surpasses the Shard in London, underscoring its prominence on the global stage. Constructed using 2,000 tons of steel and 15,000 cubic meters of concrete, the Sky Tower serves as a critical link in New Zealand's telecommunications network, featuring 21 transmission antennas. The Sky Tower can withstand wind speeds of up to 200 kilometers per hour and earthquakes with a magnitude of up to 8.0 on the Richter scale, owing to its deeply secured foundation which penetrates 15 meters into the earth. The Sky Tower's lighting, which uses energy-efficient LED bulbs, often changes color to support charitable causes, intertwining functionality with community engagement. The Yangtze River Tunnel in China is an ambitious infrastructure project designed to improve connectivity between the cities of Shanghai and Nantong. This 6.8-mile tunnel, part of the larger Shanghai-Nantong Railway project, is one of the longest underwater tunnels in the world. The construction involves the use of advanced tunnel boring machines to excavate through challenging geological conditions, including soft soils and high water pressures. One of the primary challenges is ensuring the structural integrity and safety of the tunnel, which is addressed through the use of high-strength, waterproof concrete and advanced reinforcement techniques. The project also includes the installation of state-of-the-art ventilation, lighting, and safety systems to ensure a safe and comfortable environment for passengers. Extensive environmental assessments and mitigation measures are implemented to minimize the impact on the Yangtze River ecosystem. Once completed, the Yangtze River Tunnel will significantly reduce travel time between Shanghai and Nantong, enhancing regional connectivity and economic development. The tunnel is expected to become a major transportation artery, facilitating the movement of people and goods and contributing to the economic growth of the region.
We have to travel over to Singapore next, where the Jurong Island expansion project stands. This multi-billion-dollar project involves extensive land reclamation, construction of industrial facilities, and development of supporting infrastructure. The land reclamation process at Jurong Island uses advanced dredging equipment and techniques to ensure the stability and sustainability of the reclaimed land. Cutter suction dredgers and trailing suction hopper dredgers are used to excavate and transport sand from offshore borough areas to the reclamation site. The dredged material is then pumped into designated areas where it is compacted and stabilized to create a solid foundation for industrial facilities. The construction of industrial facilities at Jurong Island involves significant engineering and logistical challenges. These facilities include refineries, chemical plants, storage tanks, and pipelines, which require extensive planning and coordination to ensure safe and efficient operations. Utility infrastructure is another critical component of the Jurong Island expansion. This includes the installation of water supply and distribution systems, wastewater treatment facilities, and power generation and distribution networks. The water supply system involves constructing desalination plants and reservoirs to provide a reliable source of fresh water to industrial plants and substations to supply electricity to the industrial facilities. The power plants are designed to use natural gas as the primary fuel source, with backup generators to ensure a continuous power supply in case of outages. In addition to the construction of industrial facilities and infrastructure, the Jurong Island expansion also involves the development of supporting facilities such as offices, laboratories, and storage warehouses. These facilities provide the necessary support for the industrial activities and ensure the smooth and efficient operation of the petrochemical hub.
We travel to Japan next, where an even taller bridge is located. Spanning the Akashi Strait, the Akashi Kaikayo Bridge holds the title of the world's longest central span of any suspension bridge, measuring a staggering 1991 meters. Standing 283 meters tall, its towers are higher than any other suspension bridge, and when compared to architectural icons, they exceed the height of the Statue of Liberty by about 93 meters. The construction of the Akashi Kaikayo Bridge was a feat of precision engineering, requiring over 1.4 million cubic meters of concrete and enough steel wire to encircle the globe 7 times. Inaugurated in 1998, the bridge was designed to withstand winds of up to 286 kilometers per hour, severe earthquakes, and harsh sea currents. This resilience was immediately tested as it successfully withstood the Kobe earthquake in 1995 during its construction phase.
Let's travel over to Australia for the WestConnex project. This $16.8 billion development involves the construction of 33 kilometers of new and upgraded motorways, including tunnels, interchanges, and expressways. One of the significant engineering challenges in the WestConnex project is constructing the extensive tunnel network. The tunnels are built using tunnel boring machines, which can simultaneously excavate and line the tunnels with concrete segments. This method ensures a smooth and efficient construction process, minimizing disruption to the surface environment. The boring machines used in the project are some of the largest in the world, with diameters up to 15.5 meters. Another innovative aspect of the WestConnex project is using smart technology to manage traffic flow and improve safety. The motorways are equipped with an intelligent transport system that includes real-time traffic monitoring, electronic signage, and automated incident detection. This system helps manage congestion and ensures a swift response to any incident, enhancing the overall efficiency of the road network. Measures have been taken to minimize the environmental impact of the construction and operation of the motorways. This includes using low-emission construction equipment, implementing noise barriers, and green walls to reduce noise pollution. One of the key benefits of the WestConnex project is a significant reduction in travel times for commuters. By providing new and upgraded motorways, the project aims to alleviate congestion for some of Sydney's busiest roads, making it easier and faster for people to travel across the city.
Let's move over to the Netherlands next for the Rotterdam Towers megaproject. Designed by the renowned architect Rem Koolhaas, the project comprises 3 interconnected towers that rise to a height of 150 meters. Construction of the Rotterdam Towers began in 2009 and was completed in 2013. The project involved a significant investment of around $550 million. One of the unique features of the development is its innovative design, which maximizes space and functionality within a compact footprint. The towers are connected by a series of sky bridges, creating a dynamic and visually striking structure. The Rotterdam Towers project aimed to create a vibrant urban community with a mix of residential, commercial, and recreational spaces. The development includes 240 apartments, 72,000 square meters of office space, a 4-star hotel with 285 rooms, and a variety of retail and dining options. The project also features extensive public spaces, including a plaza and a rooftop garden, providing residents and visitors with green areas to relax and socialize. The construction process presented several challenges, including the need to coordinate multiple building functions within a single structure and ensure that all systems were seamlessly integrated. The project team employed advanced building information modeling technology to plan and execute the construction, allowing for precise coordination and efficient use of resources. The Rotterdam Towers have become a landmark in the city, symbolizing Rotterdam's innovative spirit and commitment to sustainable urban development. The project has received numerous awards for its design and sustainability features, highlighting its significance as a model for future urban developments. The Zoji Layan-More tunnel projects in India are monumental infrastructure developments aimed at improving year-round connectivity between the Kashmir Valley and Ladakh. The Zojila Tunnel, stretching over 9 miles, is set to be one of the longest and highest altitude road tunnels in the world, providing all-weather access through the Himalayan range. The Zmore Tunnel at 4.2 miles serves as a crucial link to the Zojila Tunnel. These projects involve cutting through some of the most challenging terrains, characterized by extreme weather conditions and high seismic activity. Advanced tunnel boring machines and new Austrian tunneling methods are employed to navigate these challenges, ensuring precision and safety. One of the primary challenges is the stabilization of loose rock and soil, which is addressed through ground freezing techniques and the installation of rock bolts and shotcrete. The tunnels are designed with multiple safety features, including emergency exits, ventilation systems, and fire detection and suppression systems. During construction, extensive environmental monitoring is conducted to mitigate impacts on the fragile mountain ecosystem. The projects also involve the construction of access roads, bridges, and support infrastructure to facilitate transportation and logistics. These access routes are critical for transporting materials and workers to the remote construction sites, ensuring timely progress. Once completed, these tunnels will drastically reduce travel time, enhance trade and tourism, and improve the strategic mobility of the Indian Armed Forces in this remote region. The projects will also provide significant socio-economic benefits to the local communities, improving access to essential services and boosting economic activities. Enhanced connectivity will foster regional development and integration, making it easier for people and goods to move between these historically isolated areas. Additionally, the tunnels will improve safety and reliability for travelers, reducing the risk of accidents and road closures due to adverse weather conditions. The construction of these tunnels employs specialized machinery such as rock drilling rigs, ground freezing units, and advanced tunnel lining equipment to ensure structural stability and safety. The Punta Sierra Wind Farm in Chile is an impressive renewable energy project located in the Coquimbo region, near the city of La Higuera. This project is designed to harness the strong and consistent winds of the coastal region to generate electricity. With a total installed capacity of 82 megawatts, the Punta Sierra Wind Farm is capable of producing enough energy to power approximately 60,000 homes. The construction of the wind farm involves several critical components, including the wind turbines, foundations, and the electrical infrastructure needed to connect the farm to the grid. The wind turbines, each with a capacity of 2 megawatts, are manufactured by leading companies in the wind energy sector. These turbines are mounted on towers that are approximately 260 feet tall, allowing them to capture the stronger winds at higher altitudes. The installation of the wind turbines requires meticulous planning and precision engineering. Each turbine consists of multiple components, including the rotor blades, nacelle, and tower sections, which are transported to the site and assembled using large cranes. The foundations for the turbines are constructed using reinforced concrete, designed to support the weight of the turbines and withstand the forces exerted by the wind. In addition to the physical construction, the project also involves the installation of an extensive electrical infrastructure. This includes the construction of a substation and the laying of underground cables to connect the turbines to the substation. The substation is equipped with transformers and switchgear to manage the flow of electricity and ensure a stable connection to the national grid. The Tangier Med Port expansion in Morocco is a major infrastructure project aimed at transforming the port into one of the largest and most modern in Africa. Located on the Strait of Gibraltar, Tangier Med is strategically positioned to serve as a key hub for maritime trade between Europe, Africa, and the Americas. The expansion project includes the construction of new container terminals, logistics zones, and support infrastructure to significantly increase the port's capacity and efficiency. The construction of the new container terminals involves extensive dredging and land reclamation to create additional space for the terminals and berths. The dredging operations are carried out using specialized vessels that remove sediment from the seabed, allowing larger ships to access the port. The reclaimed land is then stabilized and prepared for construction using advanced geotechnical techniques. The new terminals are equipped with state-of-the-art cargo handling equipment, including gantry cranes, automated stacking cranes, and conveyor systems. These facilities are designed to handle the latest generation of ultra-large container ships, significantly increasing the port's throughput capacity. The construction of the terminals involves the installation of heavy-duty concrete foundations and the erection of steel structures to support the cranes and other equipment. In addition to the container terminals, the expansion project includes the development of extensive logistics zones and support infrastructure. These areas are designed to accommodate warehousing, distribution centers, and other logistics services, enhancing the port's role as a regional logistics hub. The construction of these facilities involves earthworks, concrete pouring, and the installation of utility networks to support the operations. One of the significant challenges of the 10-year Medport expansion project is coordinating the construction activities while keeping the existing port operations running smoothly. The construction teams must work closely with port authorities and operators to minimize disruptions and ensure the safety of workers and cargo. Additionally, the project must adhere to strict environmental and safety regulations to protect the marine environment and the surrounding communities. The Dunkirk LNG terminal in France is a critical infrastructure project designed to enhance the country's energy security and diversify its sources of natural gas. Located in the port of Dunkirk, the terminal has a capacity to handle up to 13 billion cubic meters of natural gas per year, making it one of the largest LNG terminals in Europe. The project includes the construction of storage tanks, regasification units, and support infrastructure to import and process liquefied natural gas. The construction of the storage tanks is one of the most complex aspects of the project. Each tank is designed to store LNG at a temperature of -260 degrees Fahrenheit, requiring advanced cryogenic engineering and materials. The tanks are double-walled structures with an inner steel tank surrounded by an outer concrete shell. The space between the two walls is filled with insulation to maintain the low temperature and prevent heat ingress. The regasification units are responsible for converting the LNG back into its gaseous state for distribution through the national gas network. These units consist of heat exchangers and vaporization systems that use seawater or ambient air to warm the LNG. The construction of these units involves the installation of advanced piping systems and control equipment to manage the flow and pressure of the gas. In addition to the storage tanks and regasification units, the project includes the construction of a jetty to accommodate LNG carriers. The jetty is equipped with unloading arms and safety systems to transfer the LNG from the carriers to the storage tanks. The construction of the jetty involves extensive dredging and piling works to create a stable foundation in the marine environment. One of the significant challenges of the Dunkirk LNG terminal project is ensuring the safety and security of the facility. The terminal is equipped with advanced safety systems, including gas detection, fire suppression, and emergency response equipment to protect workers and the surrounding communities. Additionally, the project must adhere to strict environmental regulations to minimize the impact on the marine ecosystem and air quality. Victoria Dockside in Hong Kong is a major mixed-use development project that transforms the Tsim Sha Tsui waterfront into a vibrant hub for business, culture, and tourism. The project includes the construction of office towers, luxury residences, retail spaces, and cultural venues, creating a dynamic urban environment that reflects Hong Kong's status as a global city. The construction of Victoria Dockside involves several key components, including the high-rise buildings, the waterfront promenade, and the public spaces. The high-rise buildings are designed by leading architects and feature state-of-the-art engineering and construction techniques. The towers are constructed using reinforced concrete and steel, with advanced facade systems to enhance energy efficiency and aesthetic appeal. The waterfront promenade is a central feature of the development, providing a scenic and accessible space for residents and visitors. The construction of the promenade involves extensive landscaping, paving, and the installation of amenities such as seating, lighting, and public art. The design incorporates sustainable elements, such as green roofs and rainwater harvesting systems, to enhance environmental performance. In addition to the built structures, Victoria Dockside includes the development of public spaces and cultural venues. These spaces are designed to foster community engagement and cultural exchange, with features such as open plazas, performance stages, and art installations. The construction of these spaces involves careful planning and coordination to integrate them seamlessly with the surrounding urban fabric. One of the significant challenges of the Victoria Dockside project is managing construction activities in a densely populated urban environment. The construction teams must work closely with local authorities and stakeholders to minimize disruptions and ensure the safety of workers and residents. Additionally, the project must adhere to strict environmental and safety regulations to protect the waterfront and the surrounding communities. Malacca Gateway in Malaysia is an ambitious waterfront development project aimed at transforming the historic city of Malacca into a major tourism and commercial hub. The project includes the construction of a series of man-made islands, luxury hotels, shopping malls, and entertainment venues, creating a vibrant destination that attracts visitors from around the world. The construction of Malacca Gateway involves several critical components, including land reclamation, the construction of infrastructure, and the development of tourism and commercial facilities. The land reclamation process involves dredging and filling the seabed to create the new islands, requiring advanced geotechnical engineering and environmental management. The reclaimed land is stabilized and prepared for construction using techniques such as soil compaction and reinforcement. The development of infrastructure includes the construction of roads, bridges, and utility networks to support the new islands. These elements are designed to provide seamless connectivity and ensure the efficient operation of the development. The construction of roads and bridges involves extensive earthworks, concrete pouring, and steel reinforcement to create durable and reliable structures. In addition to the infrastructure, Malacca Gateway includes the development of luxury hotels, shopping malls, and entertainment venues. These facilities are designed by leading architects and feature state-of-the-art construction techniques and materials. The construction of these buildings involves advanced formwork, steel erection, and facade systems to create visually striking and functional spaces. One of the significant challenges of the Malacca Gateway project is managing the environmental impact of the development. The project includes extensive environmental assessments and mitigation measures to protect the marine ecosystem and preserve the natural beauty of the area. Additionally, the construction teams must work closely with local communities and stakeholders to address concerns and ensure the sustainable development of the project. The Eurasia Tunnel in Turkey is a major infrastructure project that significantly improves connectivity between the European and Asian sides of Istanbul. The tunnel, which runs beneath the Bosphorus Strait, provides a vital link for both passenger and freight traffic, reducing travel time and easing congestion on the city's bridges. The tunnel is approximately 3.4 miles long, with a two-deck design to accommodate both cars and light vehicles. The construction of the Eurasia Tunnel involves several critical components, including the tunnel boring machine, the tunnel lining, and the ventilation and safety systems. The TBM is a specialized piece of equipment that excavates and installs the tunnel segments simultaneously. The machine is designed to operate in the challenging geological conditions beneath the Bosphorus, using advanced cutting and reinforcement techniques to ensure the stability and safety of the tunnel. The tunnel lining is constructed using precast concrete segments, which are assembled as the TBM advances. These segments are designed to provide structural support and prevent water ingress, ensuring the durability and longevity of the tunnel. The lining also includes features such as fire-resistant materials and drainage systems to enhance safety and performance. In addition to the physical construction, the Eurasia Tunnel includes the installation of advanced ventilation and safety systems. These systems are designed to manage air quality and provide emergency response capabilities in the event of an incident. The ventilation system includes fans and ductwork to circulate fresh air and remove exhaust gases, while the safety systems include fire detection and suppression equipment, emergency lighting, and communication networks. One of the significant challenges of the Eurasia Tunnel project is managing the construction activities beneath a busy and densely populated city. The construction teams must use advanced monitoring and control techniques to minimize disruption and ensure the safety of workers and residents. Additionally, the project must adhere to strict environmental and safety regulations to protect the marine environment and the surrounding communities. The Riyadh Metro in Saudi Arabia is an ambitious urban rail project designed to transform public transportation in the capital city. The metro system comprises 6 lines, spanning a total of 110 miles and including 85 stations. The construction of the Riyadh Metro involves advanced tunneling techniques, station construction, and the installation of state-of-the-art train control systems. Tunneling for the metro lines employs tunnel boring machines, which are large, cylindrical machines that excavate and install tunnel segments simultaneously. These machines can operate 24/7, significantly speeding up the construction process. The tunnels are lined with precast concrete segments, which are assembled as the TBM advances. This method ensures the tunnels are structurally sound and resistant to groundwater ingress. Station construction involves creating large underground spaces capable of accommodating thousands of passengers daily. Each station is designed with multiple levels, including concourses, platforms, and service areas. The construction process includes extensive excavation, concrete pouring, and steel reinforcement to create durable, safe, and accessible stations. Additionally, the stations are equipped with advanced safety and ventilation systems to ensure passenger comfort and safety. The train control systems for the Riyadh Metro are highly sophisticated, employing automated train operation technology. This system allows for driverless train operation, improving efficiency and reducing the risk of human error. The auto system is integrated with advanced signaling and communication systems, ensuring smooth and safe train movements throughout the network. One of the significant challenges of the Riyadh Metro project is managing construction in a densely populated urban environment. Engineers must carefully plan and execute construction activities to minimize disruptions to daily life and ensure the safety of workers and residents. Additionally, the extreme weather conditions in Riyadh, particularly the high temperatures, require special considerations for worker safety and construction materials. The Long Than International Airport in Vietnam is a major infrastructure project aimed at enhancing the country's aviation capacity and supporting economic growth. Located in Dong Nai Province near Ho Chi Minh City, the airport is designed to handle up to 100 million passengers and 5 million tons of cargo annually. The project includes the construction of a new terminal, runways, and support infrastructure. The construction of the new terminal involves extensive earthworks, concrete pouring, and steel erection. The terminal is designed with a modern, open layout, featuring large glass windows and high ceilings to create a spacious and welcoming environment. Advanced construction techniques, such as prefabrication and modular construction, are used to speed up the building process and ensure high-quality finishes. The runways are designed to accommodate the largest commercial aircraft, requiring precise engineering to ensure smooth and safe landings and takeoffs. The construction of the runways involves extensive earthworks, grading, and paving, using advanced materials and techniques to create a durable and reliable surface. In addition to the terminal and runways, the project includes the construction of support infrastructure, such as taxiways, aprons, and utility networks. These elements are designed to provide seamless connectivity and ensure the efficient operation of the airport. The construction process involves extensive coordination between various contractors and suppliers to ensure all components are delivered and installed on time. One of the significant challenges of the Long Than International Airport project is managing construction activities while minimizing disruptions to existing airport operations and the surrounding communities. Engineers and planners must carefully coordinate construction schedules and activities to ensure the safety of workers and residents. Additionally, the project must adhere to strict environmental and safety regulations to protect the environment and ensure compliance with international standards. The Grand Ningbo Dam in the Democratic Republic of the Congo is an ambitious hydroelectric project designed to harness the power of the Congo River and provide electricity to millions of people across Africa. Once completed, the dam is expected to have a generating capacity of up to 40,000 megawatts, making it the largest hydroelectric project in the world. The project includes the construction of a series of dams, powerhouses, and transmission lines. The construction of the dams involves extensive earthworks, concrete pouring, and steel reinforcement to create stable and durable structures. The main dam is designed to span the Congo River, creating a large reservoir to store water for power generation. The construction process includes the diversion of the river, the excavation of foundations, and the erection of concrete and steel structures to form the dam. The powerhouses are equipped with turbines and generators that convert the energy of the flowing water into electricity. The construction of the powerhouses involves the installation of advanced mechanical and electrical systems, requiring precision engineering and expertise. The turbines are designed to operate efficiently under varying water flow conditions, ensuring a reliable and continuous supply of electricity. In addition to the dams and powerhouses, the project includes the construction of transmission lines to distribute the electricity generated by the dam. These lines are designed to transport high-voltage electricity over long distances, connecting the dam to major cities and industrial centers across Africa. The construction of the transmission lines involves the erection of steel towers, the stringing of conductors, and the installation of substations to manage the flow of electricity. One of the significant challenges of the Grand Inge Dam project is managing the environmental and social impacts. The construction and operation of the dam affect the local ecosystem and communities, necessitating extensive environmental assessments and mitigation measures. Engineers and planners work closely with environmental experts and local communities to address concerns and ensure sustainable development. The Auckland City Rail Link in New Zealand is a major infrastructure project designed to enhance public transportation and improve connectivity in the city. The project involves the construction of a new underground rail line, spanning approximately 3.5 kilometers and including several new stations. The rail link is expected to significantly reduce travel times and increase the capacity of Auckland's rail network. The construction of the Auckland City Rail Link involves several critical components, including tunneling, station construction, and the installation of rail infrastructure. Tunneling is carried out using tunnel boring machines, which excavate and install tunnel segments simultaneously. The tunnels are lined with precast concrete segments, providing a durable and waterproof structure. The use of TBMs allows for rapid and efficient tunneling, minimizing disruption to the surface and surrounding areas. The construction of the new stations involves extensive excavation, concrete pouring, and steel reinforcement. Each station is designed with multiple levels, including concourses, platforms, and service areas. The stations are equipped with modern amenities and safety systems, ensuring a comfortable and secure environment for passengers. The construction process requires careful coordination to integrate the new stations with existing rail and urban infrastructure. In addition to the physical construction, the Auckland City Rail Link includes the installation of advanced rail infrastructure, such as tracks, signaling systems, and power supply. The tracks are constructed using continuous welded rail, providing a smooth and reliable surface for trains. The signaling systems are designed to manage train movements and ensure safety, while the power supply includes the installation of overhead lines and substations to provide electricity to the trains. One of the significant challenges of the Auckland City Rail Link project is managing construction activities in a busy urban environment. Engineers and planners must carefully coordinate construction schedules and activities to minimize disruptions to traffic, businesses, and residents. Additionally, the project must adhere to strict environmental and safety regulations to protect the urban environment and ensure the safety of workers and the public. The Maputo-Catembe Bridge in Mozambique is a major infrastructure project that significantly improves connectivity between the capital city of Maputo and the southern region of Catembe. The bridge spans approximately 1.6 kilometers across the Maputo Bay, making it the longest suspension bridge in Africa. The project includes the construction of access roads, toll plazas, and support infrastructure to facilitate the flow of traffic. The construction of the Maputo-Catembe Bridge involves several critical components, including the main suspension cables, the bridge deck, and the supporting towers. The main cables are made from high-strength steel, capable of supporting the weight of the bridge deck and the traffic it carries. These cables are anchored to massive concrete blocks on either side of the bay, providing the necessary stability and strength. The bridge deck is constructed using prefabricated steel sections, which are transported to the site and assembled using large cranes. Each section is carefully lifted into place and connected to the main cables using hangers. The deck is then paved with asphalt and equipped with safety barriers and lighting systems to ensure the safety and comfort of drivers. The supporting towers, which rise to a height of approximately 141 meters, are constructed using reinforced concrete. These towers are designed to withstand the forces exerted by the cables and the traffic load, as well as environmental factors such as wind and earthquakes. The construction of the towers involves extensive formwork, concrete pouring, and steel reinforcement to create a stable and durable structure. One of the significant challenges of the Maputo-Catembe Bridge project is the complex engineering required to construct such a long and high bridge over a deep and wide bay. The construction teams must use advanced surveying and alignment techniques to ensure the bridge is straight and level. Additionally, the project must adhere to strict environmental and safety regulations to protect the marine environment and the surrounding communities. The New York Penn Station expansion in the United States is a major infrastructure project designed to increase the capacity and improve the functionality of one of the busiest transportation hubs in the country. The project includes the construction of new concourses, platforms, and support infrastructure to accommodate growing passenger demand and enhance the overall experience for travelers. The construction of the new concourses involves extensive excavation, concrete pouring, and steel erection to create large, open spaces for passengers. These concourses are designed with modern amenities, including seating areas, retail spaces, and digital displays to provide information and entertainment. The construction process requires careful coordination to integrate the new concourses with the existing station infrastructure and ensure minimal disruption to ongoing operations. The new platforms are designed to accommodate longer and more frequent trains, increasing the station's capacity and efficiency. The construction of these platforms involves the installation of tracks, signaling systems, and safety features to ensure smooth and reliable train movements. The platforms are equipped with modern amenities, such as seating, lighting, and accessibility features to enhance passenger comfort and safety. In addition to the concourses and platforms, the project includes the construction of support infrastructure, such as ventilation systems, electrical networks, and emergency response facilities. These elements are essential for the safe and efficient operation of the station, providing the necessary support for passengers and staff. The construction of this infrastructure involves the installation of advanced systems and equipment to manage air quality, power supply, and safety in the station. The successful completion of the New York Penn Station expansion represents a significant investment in the future of New York's transportation infrastructure. The project enhances the capacity and functionality of the station, improving the overall experience for travelers and supporting the city's economic growth. The Copenhagen Airport expansion in Denmark is a major infrastructure project designed to increase the airport's capacity and improve passenger services. The West Link project is expected to significantly reduce travel times and increase the capacity of Gothenburg's rail network. The construction of the Gothenburg West Link involves several critical components, including tunneling, station construction, and the installation of rail infrastructure. Tunneling is carried out using tunnel boring machines, which excavate and install tunnel segments simultaneously. The tunnels are lined with precast concrete segments, providing a durable and waterproof structure. The use of TBMs allows for rapid and efficient tunneling, minimizing disruption to the surface and surrounding areas. The construction of the new stations involves extensive excavation, concrete pouring, and steel reinforcement. Each station is designed with multiple levels, including concourses, platforms, and service areas. The stations are equipped with modern amenities and safety systems, ensuring a comfortable and secure environment for passengers. The construction process requires careful coordination to integrate the new stations with existing rail and urban infrastructure. In addition to the physical construction, the Gothenburg West Link includes the installation of advanced rail infrastructure, such as tracks, signaling systems, and power supply. The tracks are constructed using continuous welded rail, providing a smooth and reliable surface for trains. The signaling systems are designed to manage train movements and ensure safety, while the power supply includes the installation of overhead lines and substations to provide electricity to the trains. The Gothenburg West Link represents a significant investment in Sweden's public transportation infrastructure. The project is expected to enhance connectivity, reduce congestion, and support sustainable urban development in Gothenburg, making it a key component of the city's future growth. Let's delve into the monumental Grand Coulee Dam project, an iconic feat of engineering located on the Columbia River in Washington state. Completed in 1942, this project was a cornerstone of the New Deal, aimed at combating the economic woes of the Great Depression while harnessing the power of the mighty Columbia River. With a final price tag of $168 million, it was one of the most expensive and ambitious infrastructure projects of its time. Construction of the Grand Coulee Dam began in 1933 and required the collective effort of over 12,000 workers at its peak. These workers faced numerous challenges, including harsh weather conditions and the logistical complexities of managing such a vast construction site. The dam stretches 523 feet across and stands 550 feet tall, making it the largest concrete structure in the United States. Its creation transformed the region, providing vital hydroelectric power and irrigation that would spur agricultural and economic development. One of the most impressive aspects of the Grand Coulee Dam is its hydroelectric power capacity. Initially, it housed 3 power plants with a total generating capacity of 2280 megawatts. Over the years, expansions have increased this capacity to over 6,800 megawatts, making it one of the largest power producers in the world. The dam also created Lake Roosevelt, a reservoir that spans approximately 125 square miles. This reservoir provides irrigation to over 600,000 acres of farmland, transforming arid regions into fertile agricultural lands. The agricultural productivity of central Washington owes much to the water resources provided by the Grand Coulee Dam. However, the construction of the dam was not without its controversies and challenges. It necessitated the relocation of thousands of people and had significant environmental impacts, particularly on fish populations and the livelihoods of indigenous tribes. The project's success required innovative engineering solutions, such as the use of massive cableways to transport concrete and materials across the site and careful management of the Columbia River's flow. It's time to explore the Crescent Dunes Solar Energy Project next, which is a groundbreaking renewable energy initiative located near Tonopah, Nevada. Completed in 2015, this state-of-the-art solar power plant represents a significant leap in solar energy technology, with a price tag of $1 billion. The Crescent Dunes Solar Energy Project was developed by Solar Reserve and is renowned for its innovative use of concentrated solar power technology. Unlike traditional photovoltaic solar plants, Crescent Dunes uses a central tower surrounded by over 10,000 mirrors, known as heliostats. These mirrors track the sun and focus its energy onto the tower, heating molten salt to extremely high temperatures. One of the key advantages of this system is its ability to store thermal energy, allowing the plant to generate electricity even after the sun has set. The Crescent Dunes facility has a capacity of 110 megawatts and can provide power to approximately 75,000 homes. Building the Crescent Dunes Solar Energy Project was a massive undertaking, requiring the coordination of over 1,000 workers during peak construction phases. The project faced numerous challenges, including logistical hurdles related to transporting and assembling the large number of heliostats and constructing the central tower, which stands at 640 feet tall. The project's location in the Nevada desert posed additional difficulties, such as extreme weather conditions and the need to protect the fragile desert ecosystem. Despite these challenges, the project was completed on time and has set a new standard for solar power plants worldwide. Let's take a look at the impressive Mercedes-Benz Stadium, home to the Atlanta Falcons and Atlanta United FC. Situated in the heart of Atlanta, this sports and entertainment facility is a testament to modern construction, with a staggering cost of $1.6 billion. The Mercedes-Benz Stadium project broke ground in 2014 and opened its doors in August 2017. Designed by Hawk, the stadium covers approximately 2 million square feet and boasts a seating capacity of 71,000, expandable to 75,000 for major events. The stadium is notable for its innovative retractable roof, which resembles a camera aperture and can open or close in just under 10 minutes. This unique design allows the venue to host events in both open-air and climate-controlled environments, providing flexibility for a wide range of activities. One of the standout features of the Mercedes-Benz Stadium is its 360-degree HD Halo video board, which is the largest of its kind in the world. This massive screen, which spans 1,100 feet in circumference, ensures that every spectator has a clear view of the action, no matter where they are seated. Additionally, the stadium is equipped with cutting-edge technology, including high-speed Wi-Fi and numerous LED displays throughout the venue. Constructing the Mercedes-Benz Stadium was a massive endeavor, requiring the efforts of over 4,000 workers during peak periods. The project faced several challenges, including the complexity of the retractable roof mechanism and the need to integrate numerous sustainable design elements. These sustainable features include a rainwater collection and reuse system, a LEED Platinum certification, and over 4,000 solar panels, making it one of the greenest stadiums in the world. Let's delve into the Northgate Link extension, a transformative addition to Seattle's public transportation network. Completed at a cost of $1.9 billion, this project is a cornerstone of the region's efforts to enhance urban mobility and reduce traffic congestion. Breaking ground in 2012 and opening to the public in October 2021, the Northgate Link extension stretches the city's light rail system by 4.3 miles, connecting the University of Washington to Northgate. This crucial extension includes 3 new stations, strategically located to serve key residential and commercial hubs in northern Seattle. A defining feature of the Northgate Link extension is the engineering marvel of its twin tunnels, constructed using state-of-the-art tunnel boring machines. These machines, dubbed Brenda and Pamela, excavated deep beneath the city, navigating complex soil conditions and existing underground infrastructure with remarkable precision. The construction process engaged thousands of workers and required intricate planning and coordination. Each new station is designed with a focus on accessibility, safety, and community integration, featuring modern amenities and public art installations that enhance the commuter experience. The Northgate Link extension significantly reduces travel times, with the journey from Northgate to downtown Seattle now taking just 14 minutes. This improvement is expected to ease road traffic and provide a reliable alternative to driving, fostering greater use of public transportation. The project's impact on Seattle's urban landscape is profound, revitalizing neighborhoods and stimulating economic growth around the new stations. It's time to explore the Kennedy Space Center, a monumental project that stands as a pinnacle of aerospace engineering. Located on Merritt Island, Florida, this iconic facility was established in 1962 and became operational during the height of the space race. The total cost of constructing and developing the Kennedy Space Center is estimated at approximately $2 billion. The Space Center spans 144,000 acres and serves as NASA's primary launch center for human spaceflight. Its construction required the efforts of thousands of engineers, technicians, and laborers working around the clock to bring this ambitious project to fruition. The center's most famous feature is Launch Complex 39, which includes 2 launch pads and the massive vehicle assembly building. The VAB is one of the largest buildings in the world by volume and was designed to assemble the Saturn V rocket, the behemoth that carried astronauts to the moon during the Apollo program. The Kennedy Space Center was not just built for the Apollo missions. It has been instrumental in numerous space endeavors, including the Space Shuttle program and, more recently, SpaceX's commercial crew missions. The facility's infrastructure includes a network of crawler transporters that move rockets from the VAB to the launch pads, a distance of about 3 miles. These crawlers are engineering marvels in their own right, capable of carrying the immense weight of fully assembled rockets. One of the significant challenges faced during the construction of the Kennedy Space Center was managing the environmental impact on the surrounding Merritt Island National Wildlife Refuge. This required careful planning and innovative solutions to ensure that the center's operations did not adversely affect the local ecosystem. To understand the scale of the Kennedy Space Center, consider that its launch pads and support facilities occupy an area equivalent to about 219 football fields. The center has continuously evolved, incorporating cutting-edge technology and infrastructure to support the ever-advancing field of space exploration. Let's take a closer look at the Second Midtown Tunnel project. Located under the Elizabeth River, the Second Midtown Tunnel connects the cities of Norfolk and Portsmouth. Its construction began in 2012 and reached completion in 2016. This project involved building a new 2-lane tunnel parallel to the existing Midtown Tunnel, effectively doubling the capacity of this crucial traffic artery. With a cost of $2.1 billion, the construction process for the Second Midtown Tunnel was both innovative and complex. Unlike traditional tunneling methods, this project used an immersed tube technique. Prefabricated tunnel sections, each weighing approximately 16,000 tons, were constructed in a dry dock. These sections were then floated to the site, submerged into a pre-dug trench on the riverbed, and connected to form the tunnel. This method minimized disruption to river traffic and ensured precise alignment of the tunnel sections. The new tunnel not only alleviates traffic congestion, but also enhances safety and travel times for thousands of commuters. In terms of environmental considerations, the project included several measures to mitigate its impact. This included careful monitoring of water quality during construction and the use of innovative techniques to manage and minimize sediment displacement. The Second Midtown Tunnel also features modern safety enhancements, such as advanced ventilation systems, state-of-the-art lighting, and emergency response facilities. These upgrades ensure the tunnel meets contemporary standards for infrastructure resilience and commuter safety. Comparing this project to other major infrastructure endeavors, the Second Midtown Tunnel stands out for its strategic importance in regional connectivity and its use of advanced construction techniques. Next, let's explore the Las Vegas Convention Center expansion. With a total investment of $4.3 billion, this expansion project significantly enhances the capabilities and allure of one of the world's largest convention centers. Officially completed in 2021, the Las Vegas Convention Center expansion spans 1.4 million square feet, adding substantial new space to the existing facility. The project includes the new West Hall, which alone provides an additional 600,000 square feet of exhibit space, complemented by a stunning 14,000 square foot outdoor terrace offering breathtaking views of the Las Vegas Strip. One of the most innovative aspects of the expansion is the integration of the LVCC Loop, an underground transportation system developed by Elon Musk's The Boring Company. This system features autonomous electric vehicles that transport attendees between the convention center's different halls at high speeds, significantly reducing transit times across the vast complex. The expansion was driven by the growing demand for large-scale event spaces in Las Vegas, which hosts numerous high-profile conventions, trade shows, and corporate events annually. Construction of the expansion required the coordination of thousands of workers and the use of cutting-edge building techniques to ensure that the project met its ambitious goals on time and within budget. Despite the challenges posed by the pandemic, the project team implemented rigorous health and safety protocols to keep the work on track. Sustainability was also a key focus of the expansion, with the new West Hall designed to achieve LEED certification for its environmentally friendly features. These include energy-efficient lighting, water-saving fixtures, and the use of sustainable materials throughout the construction process. In addition to the increased exhibit space, the expansion features advanced technological infrastructure, including high-speed internet and state-of-the-art audiovisual capabilities to meet the needs of modern events and exhibitions. It's time to delve into the American Dream Meadowlands, a massive entertainment and retail complex located in East Rutherford, New Jersey. With a staggering cost of $5 billion, this ambitious project represents one of the largest mall developments in the United States. Officially opened in phases starting in 2019, American Dream Meadowlands covers approximately 3 million square feet. One of the most striking features of American Dream is its Nickelodeon Universe theme park, the largest indoor theme park in the Western Hemisphere. Adjacent to this is the DreamWorks Water Park, which boasts the largest indoor wave pool. The project faced numerous challenges during its development, including financial difficulties and multiple changes in ownership. Originally conceived in early 2000, the development stalled several times due to economic downturns and funding issues. Despite these setbacks, the project was revitalized and eventually brought to completion, marking a significant milestone in the region's commercial landscape. American Dream's indoor ski slope, known as Big Snow, is another highlight of the complex. It is the first indoor real snow ski and snowboard park in North America, offering year-round winter sports activities. This unique attraction allows visitors to enjoy skiing and snowboarding regardless of the season, making it a significant draw for tourists and locals alike. The construction of American Dream Meadowlands required the coordination of thousands of workers and involved complex engineering and architectural solutions to create its diverse range of attractions. The developers also focused on sustainability, incorporating energy-efficient systems and environmentally friendly practices throughout the complex. The project's strategic location near New York City and major transportation hubs enhances its accessibility, attracting visitors from across the region and beyond. It's time to discuss the next megaproject. Welcome to the Treasure Island redevelopment in San Francisco. Set on a man-made island in the heart of San Francisco Bay, this project is transforming a former naval base into a vibrant residential and commercial hub. Treasure Island spans approximately 405 acres. To put that into perspective, it's roughly the size of 300 football fields laid side by side. The project's budget is a whopping $6 billion, earmarked for creating over 8,000 homes, of which a quarter are designated as affordable housing. The plan includes schools, hotels, and over 300 acres of parks, which means green space is central to the island's new identity. Construction began in 2011 and is set to continue in phases through 2035. The scale of manpower and machinery on this site is staggering. At its peak, the project employed thousands of workers, each skilled in various aspects of construction, from engineers and architects to builders and landscapers, all converging to bring this vision to life. One of the most intriguing aspects of the Treasure Island redevelopment is its commitment to sustainability. The island is poised to become one of the most eco-friendly developments in the U.S. with advanced stormwater systems, zero-waste goals, and buildings designed to lead gold standards. But it hasn't been all smooth sailing. The project has faced its share of challenges, from concerns over rising sea levels to remediation of the soil, which was contaminated during its days as a naval base. These issues required innovative solutions such as elevated land to combat potential flooding and extensive cleanup efforts to ensure the safety and sustainability of the new community. The amount of soil moved and treated for the redevelopment could fill over 60 Olympic-sized swimming pools. And if we talk about the infrastructure, the main roadway spanning the island's length is akin to laying down nearly 3 Golden Gate bridges end-to-end. Next up, let's delve into the monumental Houston Metrorail expansion project, a $7.5 billion undertaking that aims to revolutionize public transit in Houston, Texas. Spanning an impressive 20 miles of additional track, the Metrorail expansion is designed to connect more neighborhoods and increase accessibility across the city. The project involves intricate construction phases, which began in earnest in 2021 and are scheduled to reach completion by 2028. Over the course of these 7 years, the landscape of Houston will see transformative changes. Houston's flat and expansive geography presents unique challenges. Engineers are continuously combating the city's soft soil, which is prone to shifting and sinking. This has led to the innovative use of deep concrete pilings and reinforced steel to ensure the stability of tracks and stations. The project also incorporates elevated sections and raised platforms, designed to withstand Houston's frequent floods, thereby safeguarding the transit system's operational integrity during severe weather conditions. Each new station along the expansion route is being built with more than functionality in mind. They are envisioned as community hubs, equipped with modern amenities, real-time travel information, and artwork reflective of local culture. Despite the benefits, the path hasn't been entirely smooth. Issues ranging from logistical challenges, such as coordinating with existing traffic and utility lines, to public opposition concerning construction disruptions, have tested the project's resilience. The project management team has had to innovate on the fly, employing cutting-edge construction techniques and real-time problem-solving to keep the project on track. Specialized construction methods like the use of silent piling technology to minimize noise in residential areas and the application of advanced GPS and GIS for precision in layout and execution highlight the technical sophistication of this expansion.